Okay, we're good to go. So thank you all for coming. Good morning. Today we'll be talking a little bit about what's actually happening when we are dealing with flows and processes at the micro scale. But first I'd like to apologize looking a little bit casual today. I had some very trustworthy intelligence that there may be paint and dye stuffs being spread around today around campus. So I was advised to get a t-shirt that could get colored and full of paint. So I'm not sure what's going to happen today, but I'm very excited to learn more about the traditions around Holi. And for all of you, tomorrow we'll all have a day off, and I'd like to wish you a happy Holi.
Same to you.
So yesterday was a tough day. There were lots of equations, lots of mechanisms, but I hope that at the end of the day, doing the simulations and playing with that, actually consolidated all the information with the trust. It was all valid and built on first principles. And you could then apply that in the different software packages in order to either design but also understand the mechanisms behind electrophoretic separations. By the end of the day, it is a physical process. It is driven by equations we understand really well. And because there's so many equations involved, we need these simulation packages to calculate what's happening. But once we've got these calculations happening, it makes the understanding develop a lot faster when you can do it on your computer than when you would be in a laboratory with an instrument making up 20 different buffers and optimize your separation. So if you're not a big fan of equations, and we just had a little conversation here offline, if I need equations, I'm good at that in the morning till about 11. If I need them, I can write them down, work them through. The later it gets in the day, the worse I get with equations. So you don't necessarily need to be an engineer and absolutely comfortable around all of the equations. All you need to do is understand that what you're doing is based on equations. You can get back to the basics if you need to, because they can help you predict what's going to happen, and with that design your experiments. Today will probably be our last day of equations. So today we'll be talking about different types of actions we can do with the flow, because flow behaves very differently when we work on the micro scale than it does in everyday living. I didn't have my animations switched off yet, so let's stay here. So we need to understand when we're talking about a microchannel what's small. And if we've got a microchannel that's got a certain size determined by the characteristic length, the characteristic length is 4 times the surface area, so the width times the height, divided by the perimeter. The engineers really like normalizing conditions. Just see if I can quickly switch the animations off, because that's otherwise. Where was that? No. I'm not sure where I can switch it off. I'll look at it later because a couple of my slides, the automated timings in there. But yeah, normalizing parameters is very useful, because that means that you can move from a rectangular channel to a square one, and your physical models don't have to change. If we think about that, it is important volumes by the size to the power 3. So if we go from a cubic decimeter, which is a liter, to a cubic centimeter, that's a milliliter. So we've got a factor of 1,000 here, 3 orders of magnitude, by just dropping 1 order of magnitude from a cube that is a decimeter by decimeter, so 10 centimeters by 10 centimeters, to a cube that's a centimeter by centimeter by centimeter. We go from the total volume there from being a liter to being a milliliter. If we then go another order of magnitude down in our dimensions of our cube, we end up with a cubic millimeter. Again, we take 3 orders of magnitude in our volume there. So we have a volume of a microliter, which is kind of as small as we can easily, comfortably see. If you look at the microbiology labs, there are the autopipettes. There's wide pipette tips. You can go down to maybe half a microliter. But a microliter is still something you can comfortably see. Smaller volumes become really hard to see, but the scaling works the same. So if you go to a tenth of a cubic millimeter, we end up with nanoliter volumes. If we go even smaller, we end up with picoliters, all the way down to the point where we go to 1 cubic micrometer, which is kind of the order where we're working in microfluidics. Our channels are typically 20, 50 micrometers wide and high. So this is the order where we're working, which means that we're working in the order of femtoliter to picoliter volumes. This is where we know how things scale. We're another 3 steps down. So that gives you a little bit of an idea how small the scale is that we're actually doing our chemical experiments with when we're working with microfluidics. This was the other graph that we already looked at on Monday that shows graphically slightly differently, where we've got the scale going from meters, millimeters, micrometers and nanometers. We are with microfluidics typically in this area up to about 500 microns. So this is where we're working, which is at that femtoliter nanometer volume. It is all the same area. So we start up in a size where actually we work very well with cells and manipulate single cells because our structures are at a similar size to what the size of the cell is. So, but yeah, please keep in mind the volume scale down, and we're typically high to low microfluidics. When we're working at small scale, it means that it starts to matter and diffusion becomes faster. So here we've got a human hair. It's 200 micron in depending on ethnicity. I've got very thin hair, so my hair is probably 5. Your hair may be a lot thicker, close to 150 to 200 micron. It's the size of a grain of sand. So if you look closely, you can see it, but it is hard to start distinguishing the detail. We know that the distance that a molecule diffuses depends on the square root of the diffusion constant multiplied by the time. And the diffusion constant in turn is a function of the size of the molecule. So larger molecules diffuse a lot slower than smaller molecules. If you look at an antibody, which is small relative to acetate, it's a protein, and its diffusion constant is about 40 square micron per second. It's a small molecule, for example acetate, but you can take any small molecule drug, pharmaceutical. The diffusion constant is about 1400 square micron per second. So we have, if we let our molecules diffuse freely, we have a significant difference in the speed at which our molecules randomly diffuse. If we start off with a mixture of an antibody and a small molecule, and we come back after our antibody will be kind of close by to where we originally deposited it, because its radius will be about 40 square micron, where it has been able to diffuse to. Whereas our acetate is all over the shop, orders of magnitude further ahead. So the acetate will diffuse in the same amount of time a lot further than our large molecules like our antibodies. So in 5 seconds, the antibody can move over a distance of 20 micron, whereas the antibody will cross 100 micron, which directly provides a great opportunity for some level of separation. Because if you want to remove your acetate from your antibody, you could actually take resample close to the location where you started, and there will be a lot of your acetate will be further away than your antibody. At the same time, if for example we want to do an immunoassay and we have a microchannel that is 100 micron wide and our antibodies are sitting at the surface. For an antibody, it takes 125 seconds to reach the surface. But for a small molecule, it only takes 3.6 seconds. So again, we can manipulate our surface interaction of our molecules if they're from the center of the channel. Because if we stay shorter than a minute in the channel, the antibody is very unlikely to even see the walls when it started at the middle. Because it takes 125 seconds by diffusion to get to the outside. So that's molecular property, predictable, and we can work with that, trying to separate small and large molecules. But we can also take it to calculate what the time is that we need for an immunoassay. And this 125 seconds to cross 100 micron is why, if you've done ELISAs in molecular biology, why you need to wait so long in a microtiter plate. Because the dimensions in a microtiter plate are not even in micrometers, they're in millimeters. And you need to have times for your antibodies and antigens to find each other and bind. And that takes time, so that's why the long incubation times are required to allow diffusion to take its time, take away. If we look at flow, at the micro scale, we are typically looking at turbulent flow. Here you can see some smoke example. So this is some particles released into the air. And you can see that there's all kinds of eddies and swirly whirlies, because the particles, based on differences in velocity in the air, will go everywhere. Same when we look here at a garden hose. If the water comes out of a garden hose, it doesn't necessarily go into a straight line. You can see the very similar swirls as we know from the smoke. We can also see them in water. If we look at a river that's flowing, and you put a little stick in, you can see that the stick doesn't necessarily move in a straight line, but there's all kinds of curves in there, and they are caused by convection. When we work at the microfluidic scale, however, our flow is laminar. Which means that all the flow lines, and therefore particles or solutes, move along smooth paths and lines in an area where the viscous forces are the key players and the inertial forces are negligible. The inertial forces were the ones that caused all the swirly whirlies. We can get rid of them. Again, hard to imagine, but if you think about honey, honey's got a very high viscosity, and therefore it is really hard into honey. So honey is so water in a microchannel at a small scale, and again we'll be going through some equations after this to show the underpinning physics. But water in a microchannel behaves very similarly to honey in a jar. And if you've got some food dye, we've got a day where we're doing a lot of things with dye anyway. If you try to mix some food dye in a jar of honey and you try to stir the spoon, you'll actually see that the dye that you're trying to mix in exactly follows the path where you're dragging your spoon through, and it is not going around like your milk would be normally when you're stirring your tea. So any of the processes that we're talking about in water, think that this water in a microchannel behaves like honey, because that is something that we know about at an everyday. So the Reynolds number is one of these dimensionless numbers that we like to talk about. And if we have defined by this Reynolds number. And under a Reynolds number of about 2000, the flow is considered laminar. So you can calculate your Reynolds number in a system based on this velocity, the viscosity, and the length of the system working in. So the Reynolds number is the ratio of the inertial forces over the viscous forces. And that is then the product of the density, which as a chemist you're comfortable with, the linear velocity, so the speed with which you're moving, the characteristic length, and again that is that weird thing that we started off to be able to work with cylindrical, square and rectangular channels. So that says something about your geometry and the size of your channels, divided by the dynamic viscosity. So the Reynolds number you can calculate if you understand your fluidic properties and you know that the speed that you're moving at. If we go through an example, and here turbulent flow, we've got our swirly whirlies, that is the convective mixing. Think about the smoke, but also think about if you're pouring some milk in your tea, you can see the milk swirling around, so that is turbulent flow. We are now thinking about laminar flow, and if we do the calculations, we've got the equation here. If we've got water, the viscosity of water is about 9 to the minus 4 pascal second. The density is 1 gram or 1,000 kilos per cubic meter. So if we've got a tube that is 10 by 10 by 10 centimeter, and we're stirring at a speed of 10 centimeter per second, which is something that you'd be doing by cooking. The Reynolds number in this instance is 11,000. It is our everyday life, and indeed, if we work in our everyday life, we are in the turbulent flow, because 11,000 is larger than the 2,000, which is kind of the cutoff point for being turbulent flow if you're larger, laminar flow if you're lower. However, if we go to a channel that is 100 micron by 100 micron, still working with water with exactly the same properties, where we've got a density of 1,000 kilos per cubic meter and a viscosity of 9 times 10 to the minus 4 pascal seconds, only by downscaling from 10 by 10 centimeter to 100 by 100 micron, our Reynolds number all of a sudden drops. We're working at the same velocity. Our Reynolds number drops to 11, which is significantly smaller than 2,000. So our flow behavior changes into the laminar flow regime. I already mentioned honey, and honey has got a greater density than water. The density of honey is 1,420 kilograms per cubic meter. It also has got a larger viscosity, about 14 pascal seconds. And that's what we know, honey is a lot more viscous than water. In a 10 by 10 centimeter tub, again stirring at exactly the same velocity, our Reynolds number is 1. So our Reynolds number is significantly below 2,000, and therefore we're in the laminar flow regime. So that's where my hypothesis or my idea came from, that we can consider water in a microchannel in a fluidic context like honey in a tub or a jar that we are using at home. So processes, it's a lot harder to stir things through, it's a lot harder to get proper mixing, but if you put some dye in, you can actually trace your tracks because your fluid is not going to be moving anywhere. One of the ways that we've used this slow diffusion is that you can have liquids sitting side by side. So this here has been a hydrodynamic injection system that we've developed a couple of years ago, where it was a capillary electrophoresis system, so just ignore the channels coming to the sides for the separation. At the moment we're looking here at the center part where we introduce the flow. So we've got a sample flow here coming from the bottom, and then we've got 2 bits of buffer flow to shield the sample flow. Because we're in the laminar flow regime, these two flows will actually stay alongside each other, and we've got a picture coming up shortly. At the point that we want to inject the sample, we can stop the buffer shield flows, which means that our whole flow then is for a very small amount of time only our sample, and we can introduce a small amount of that sample into our separation channels. Then we clean everything up, so we stop our sample, we put our buffer all the way through, and then a separation can be run. So you can use these shielding flows of one reagent to prevent the diffusion of your sample into your separation system, just by the fact that the diffusion flow is laminar and all the transport is governed by diffusion, which particularly if you talk larger molecules is a really slow process. Picture says 1,000 words. So this is how the system that we just talked about looks like. Here we've got the sample represented by a red dye. Here you can see two different other solutions, the yellow dye and the blue dye. And you can see that our flow is laminar. There's nothing in this channel. So this is just a channel that's got a certain width. The flows are being pumped in at certain rates, and the rates then determine the width. The ratio between the rates determine the width that these flows will be present in the channel. So we've got the central dye is not going to be able to enter this separation channel because there's a shield in place, and we don't need to create any obstacles. We can just use the fluid dynamics to control what's happening. If we stop the buffer 1 and buffer 2, then the red comes here at the interface and we can inject a small amount of sample. Here you can even see that that's just happened. There's a small amount of the sample that was introduced before. And these curtains stop any transport because we are the laminar flow regime. Liquids just follow a nice straight line, and you can predict it based on the flow rate ratios. This is used in a functional element that's called the H filter. In the H filter, we've got a sample coming in with some large molecules and some small molecules. So that's called our donor phase. And we've got a channel that's called our acceptor phase that just contains some buffer. There's nothing sitting here in the middle. There's no membrane, no filter. It is just, this is an empty channel. But because we're in the laminar flow regime, at the point that our buffer and our sample come in, they're both going in a straight line, they don't look around, they don't go wandering and shopping. Laminar flow regime, they just go straight on. So we've got parallel flows here of our sample and our buffer. But if our sample contains both our acetate that we looked at earlier that diffuses really quickly, and it contains our antibody that diffuses really slowly, we actually will get a fair amount of diffusion of our acetate into our acceptor channel, whereas our protein stays confined to our donor channel. This way we can remove the small molecules or dilute it down to kind of equal concentrations. So we can conduct dialysis. We can remove small molecules from large molecules without the need for a membrane, just relying on the difference in diffusion constant between a small molecule and a large molecule. So there's a whole wide range of different approaches where you can use an H filter, you can extract if you want to work, so think about applications in agriculture. If you want to work with an environmental sample where there's colloids and particulate matter, the diffusion constant of that will be even lower than that of the target analytes if they're small molecules. So you can use this for sample preparation where your colloids stay in your donor phase, but your analytes are extracted into your acceptor phase. So without the need of filtration, which for colloids is not easy to do because they're so small, you can still extract your small molecule analytes without the need for any physical barriers, only relying on fluidics. This picture here I thought was quite appropriate to put in there considering we're in a visual arts environment. The Forge Lab, Albert Forge works in, I think it's Massachusetts, somewhere in the US. And he's realized there's actually really beautiful phenomena that you can do with microfluidics. So in this instance, he has a device with a number of different valves where you can control the fluidics. But you can very nicely see that the flow lines stay separated. So if you've got different dye molecules, the flows stay separated. There's no need to have physical barriers in place. Up to the point here you can start seeing a little bit of diffusion taking place. But here you can see the flows come in and they just follow their track, just like their trains, just like the guide rails in place. And all it requires is some complex plumbing. So this is another nice photograph where you can see little blunt injection needles, some flexible tubing to connect with the fluidic features, as well as here with some of the fluidic control lines. You can see the different colors are coming in. And then here, if you would zoom in, you can see all the colors segmented nicely in a zebra-like pattern, because the only thing they do is follow the flow lines. Flow rate and pressure. We already touched on this on the first day. We can predict what our flow rates are doing. We can, based on their resistance, following the same equations that we're used to use for electric circuits. So we can have flow resistance in series, which means we can add them up. We can have flow resistance in parallel, which means we can still add them up, but we then need to do 1 over, the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. Works exactly the same way for flows as it does for electrical resistances. We can calculate the flow resistance for different channels. In a cylindrical channels, the flow resistance increases with R to the power 4, whereas for a rectangular channel, it increases with the width of the channel times the height to the power 3. So we can calculate what the hydrodynamic resistance is, and that way we can calculate the resistance ratios, and the flow will divide according to our resistance ratios. So if one channel has got, as we've seen the example on Monday, 1,000,000 times the flow resistance of the other, there won't be any significant amount of liquid entering that channel because the resistance is too high. Like with an electrical system, all the current will take the easy way and take the low resistant pathway. The flow does the same thing. The flow will always follow the easiest way, so the channel with the lowest resistance. One of the nice examples that the Mans group used early in the 90s to explain that flows and currents work exactly the same way is that they got the map of London made as a microfluidic device. So all the roads in London became channels. And they then connected 2 different points to try to find the fastest way, because that was the easiest way to go from A to B. And indeed, they could, using the different solutions, they could find the fastest way in London to get from A to B, just using the fluidics of the traffic in the city. So, in microfluidics, our flow is very different to what we're used to. We are in laminar flow, flow goes in lines. Our flow resistances determine the direction that our flow is going and the ratios in which if we enter different flows into our device, we can use the flow resistance and the pressure that we apply to control the direction where our flow is going and the width. The second thing that I would like to bring your attention to is that the surface effects are a lot more pronounced when we work at the micro scale than when we're working at the large scale. And we already knew that from biology. If we look here at an elephant, and it's a little bit hard to see, but we'll get copies of the slides later on and then you can see that. This is an elephant. An elephant has got a very low surface to volume ratio. Elephant is really big and doesn't have a lot of skin to count for that. Whereas a mouse and a rat actually have got a much higher surface to volume ratio. So here we've got the body weight and here the metabolic rate. a mouse needs to work really, really hard to keep alive, to temperature control itself. Whereas for an elephant, it's not that important because the heat loss in an elephant, relative to its body mass, is a lot lower than for a mouse. So a mouse therefore needs to eat a lot more in order to compensate for the heat loss that it's got. In our normal beakers that we're working with in the lab that we're doing our synthetic reactions in, we're working in elephants. So it takes a while to get your solution warmed up. But once you are around 50 degrees, it actually takes a little bit to have that temperature change again. Because we don't have a lot of surface that we can lose our energy from compared to the volume of water that we've got in a beaker. If we look in microfluidics, we've got a lot of surface area and only a very small volume. So if we've got a picoliter droplet heated up to 50 degrees Celsius in a laboratory that's 25, before we even start our experiment, the droplet is already back at 25. The heat loss through the wall, through the thermal conductivity, because we've got such a big surface area, the heat loss in that droplet is so fast that we really need to have a good temperature control system in place because our surface to volume ratio is so high. So the good thing is we can do really, really fast PCR microfluidics because we can heat something up with a laser or a heater, a resistive heater under the channel. It doesn't take a lot of effort to heat a picoliter of liquid. We don't need a lot of calories, we don't need a lot of energy input. It also cools down really quick, so we can withdraw the energy really quick as well. So we can do sub-seconds. I think I've seen cycling times of 10 milliseconds in PCR because we can control the temperature so well because of the high surface to volume ratio when we're working on microfluidics. Much, much easier than when we're working in an Eppendorf tube, a lot easier than when we're working in a 1 or 2 liter beaker. So the surface to volume ratio, if we want to look what our ratio is, if we work in a normal beaker, kind of 10 by 10 by 10 centimeter scale, if we translate it to a cube, our surface to volume ratio is 60 per meter. So if we've got 60 times the volume per meter surface area. When we work at the micrometer scale, it is 600,000. So we've got 60,000 more. Our surface to volume ratio is to 10,000 times more when we're working on the micrometer scale than it is when we work on the centimeter scale. That is where our gains in efficiency come in. Next concept is capillarity, which we all know when you put a straw in water. We have, and it's a little bit pale here with the light on the slide, but here we've got a tray of water and we've got a glass capillary. Glass is hydrophilic. So the liquid will creep up by capillary pressure up this tube to a certain height. If we change the surface to volume ratio, we go to a narrower bore tube, the amount of pressure we can generate by this wetting on the wall significantly increases, which means that our filling increases, our capillary filling height increases when we shrink down the diameter. To start thinking about all those observations, how to put that into rules and parameters. There is the capillary number, and the capillary number is the ratio of the viscous forces and the interfacial forces. Interfacial forces with a larger surface to volume ratio become more important. The capillary number is the dynamic viscosity multiplied with the velocity. So everything in microfluidics tends to depend on how high you put your pump. So what is your flow rate? And the surface or the interfacial tension. So if we increase the capillary number, that means that we decrease the surface or the interfacial tension, which means that we increase the droplet diameter, because it's sitting more away from the surface. That is important to know when you're making droplets as small chemical reagent containers. If we've got a carrier flow and a sample flow coming in a droplet system, our carrier is an oil, so it is mineral oil, whereas our sample is aqueous, it's water. Water and oil don't mix, so they will form separate phases. There's the bug. At a certain flow rate regime, we get very nicely plugs or droplets being formed of our dispensed liquid. If our flows get too high, however, our capillary number changes, and we end up in the laminar flow regime where our water and our oil phase are flowing alongside each other. So it is important to understand what the capillary number of a system is, to understand if you want to do reactions in droplets. You don't want to be ending here, you want to be sitting here. So you can calculate what your capillary number is to know that you're working at flow rates that are in the plug regime, which means that you get stable droplets being formed. So the capillary number is the ratio of the viscous and the inertial forces. We've got a large surface to volume ratio, which means that our surface effects are really important. The surface tension can result from the deformation of the free liquid surface, so that's what we've seen in capillary. And by capillary action, we can actually drive fluidic motion, not only up in your straw, but we can also use the capillary forces to have passive microfluidic devices where the flow is controlled by having either different circuit geometries or coatings in place that manipulate the surface tension of the liquid that's flowing there. So capillary forces can draw liquid into wetting channels when the interfacial energy between the wall, the solid, and the liquid is lower than the solid gas interface. So we need to displace the gas that's present in the empty channel with the liquid, and that depends on the capillary forces if that works or not. So surface tension, we've got a couple of different regimes. When we've got hydrophobic material and we've got an aqueous droplet, it beats up. It doesn't like touching the surface. Of hydrophobic surfaces don't like water. If we've got a hydrophilic coating, our water nicely spreads on the surface. So if we treat a glass slide with a little bit of sodium hydroxide, it gets deprotonated, it becomes really hydrophilic, and you get your water just to spread all over the surface. Very different to when there's a greasy coating on. So if we've got a complete wetting, we've got a contact angle of 0. And we've just got a smooth, even film of liquid sitting on the surface. If we have a low surface tension, we get a droplet being formed where the contact angle is smaller than 90 degrees. And then the more, if this is an aqueous droplet, the more hydrophobic the surface gets, the more the droplet starts beating up. So contact angle smaller than 90 degrees, at 90 degrees, and if we go to hydrophobic, we end up with the droplet having very little contact with the surface and all held together by the cohesive forces. No need to memorize all the different constants, but I thought it was good to have a look at what the differences in surface energies are of different liquids, water and some organic solvents as well as blood, and what the contact angle is of water on, for example, fused silica. It's 52 degrees, so just over the 90 degrees. On untreated glass, gold is very hydrophobic, so contact angle is 0. And water on platinum or PMMA or glass, so our contact angle of water or the liquids change with the material properties. So hydrophilic is defined as a surface that water can wet, which means that the contact angle is below 90 degrees. A hydrophobic surface is a contact angle that doesn't wet, which is a contact angle over 90 degrees. Super hydrophobic is when you're over 150 degrees. So then there's very little contact left. A volume of an incompressible liquid minimizes the free energy, which means that the shape becomes a sphere if there is no reason to wet the surface. But with the gravity, there we will be able to pull, it will deform, but this length is in the order, for water air, it's in the order of millimeters. In microfluidics, we're way under that millimeter size, so gravity is not really a concern. Our liquids are not really affected by gravity in the spatial domain where we're looking at in microfluidics. One of the things that we can do with an electrode is change the wetting. So we can add charge to the surface and therefore make it more wettable. And that way you can move a droplet uphill. In this case we've got a hydrophilic region and hydrophobic region with an oil droplet. If using a potential difference we can change this barrier, the oil droplet will actually try to creep towards the hydrophobic region, defying gravity. So there's some nice movies that I didn't manage to get one downloaded, but where you can actually use digital microfluidics on a flexible substrate, and you can just have droplets by manipulating the voltages moving up the hill, defying gravity based on the fact that they're small, and changing the properties, the material properties, using a potential difference. Here that's explained. So here we've got a conductive droplet. If the potential is off, the droplet will be with a contact angle of about 90 degrees. So that's the initial droplet shape when there's no potential being applied. If we apply a potential droplet, then all of a sudden the contact angle changes, and our droplet will be spreading a little bit more over the electrode, which has got a whole range of applications in dispensing, moving liquids. There's digital droplet microfluidics. We already discussed very briefly about a capillary rise, where we get the smaller our capillary is, the higher, the further the liquid will progress. Again, this is governed by some equations. So when the dimensions of the tube radius are smaller than the length, the curvature can be calculated by the radius divided by the radius of the channel and the contact angle of the liquid. And you can use that to calculate if the liquid will indeed rise in your channel based on the wetting, or if it's poorly wetting, the air will actually push the liquid down into the microchannel. How far liquids can enter depends all on the material properties and the liquids that you're working with. But you can calculate how far the liquids will come, how far the capillary rise will be, based on the contact angles between your liquid and your material and the dimensions of your channel. So if we've got 100 micrometer channel, we can expect the capillary lines. We can expect if we put a droplet into a microchannel, enough is happening that it will fill the channel for about a 4 millimeter length. If we scale that capillary down to about 10 microns, so a much narrower channel, the capillary rise is longer, and in this instance, we will be able to fill 4 centimeters, 40 millimeters of our channel with our liquid. So we can pump, fill our liquid without needing to do anything at all, just by capillary rise. A very long channel, we can fill it with water. Glass is even more hydrophilic than PMMA, and for the same glass channel, if we do the calculations, we can fill 132 millimeters of capillary network, displacing air by liquid, just using the surface tension and the interaction between the water and the contact angle of water with glass. So again, these equations mean that you no longer need to be surprised if you put a little bit of liquid at the channel entrance, that all of a sudden your liquid starts moving into your channel. Your channels, typically you don't need to put a lot of effort in filling your microchannels. If your channel wall is slightly hydrophilic, your aqueous solution will just wick everything in seconds all the way through. So in summary, for scaling in microfluidics, our flow is determined by our Reynolds number. Our Reynolds number, if it's low, under 2000, it means that the viscous forces dominate and we are in the laminar flow regime. And that means that mixing becomes a challenge. Hence, our next session, after hopefully we'll have some tea, will be about how we can actually affect mixing. Because we've now looked at separating molecules because of laminar flow. Of course, we've got a difficulty arising with that, is that if we can separate things based on laminar flow, how are we ever going to mix two different reagents together? Because if we've got two reagents coming in together and they flow, we may be able to do some nice synthesis on the boundary, but our two reagents are not automatically going to be mixing. So we need to come up with a whole new toolbox to facilitate mixing in microfluidic devices, because we are in the laminar flow regime. The other important part is the surface to volume is much higher in microfluidic systems than in our normal labware that we work with as a chemist. This means that we get much more efficient heat dissipation. So we need to have a good look on our temperature control. If we do some synthesis and we've got an exothermic reaction, locally it can actually get really hot and it won't be mitigated by the rest of the thermal mass of the container we're in, because we've got very little thermal mass. Surface effects are also very important. They're important for the wetting. Wetting helps us, so if we have water and a hydrophilic channel, we don't need to put a lot of energy, we don't need to overcome any energy barriers, and our channels will just fill automatically. If we've got a hydrophobic channel, however, it will become harder and we may need a vacuum to drive our fluids into the capillary. So understanding your liquid, your fluid that you're working with, if that's a water or an oil, and understanding the material that your chip is made from. And on Monday we'll be looking at a couple of different microfabrication methods where we also go look at material choices. If you want to have, don't use any pumps and you want to work with aqueous solution, you'll probably want to select a substrate that is hydrophilic, because that means that your surface forces will just take charge of your filling of your channel and you can work with your devices that way. So surface effects are very important in microfluidics. It means that we're more prone to fouling, so we may need to have surface coatings in place. But there's a whole separate field that we're not touching on, which is capillarics, where you can use different coatings and channel geometries to just have complete assays taking place autonomously. That is the lecture on the fluid dynamics. I think it's good to take a little break before we go to the next lecture on mixing. And after the mixing, we'll go for lunch. And then we'll do a little bit on particle separations before we start celebrating Holi. So, thank you very much. I'm not sure if we've got morning tea or not. But I'd suggest we take a 10-minute break anyway to relax our brains a little bit. Thank you very much for listening, and if there's any questions, please do so.
Micro scale, the things are totally different from the bulk.
Yeah, and that's, again, it's painful when we have to go through, look at all the physics. But it also gives us a very interesting toolbox, because a lot of the behaviors provide a lot better control.
With the help of equations and examples, it was quite easy to understand the
Yeah.
difference at the micro scale and at the in the bulk.
Yeah, and I think by then if you get the textbook with it, if you're wondering about something, you can mainly use it as a reference book to just look up what the physics is.
Yeah.
So it is, and yeah, we need to So I hope you all had a nice cup of tea. And after some fundamentals, I'll recap the highlights again to realize what we're doing. And then we start looking at how we can mix different fluids at the microscale. I put this slide in here again because you can't see it often enough how small the volumes are that we're actually working with. So if we work at the centimeter scale, we're typically working with milliliters to liters in terms of volumes. Whereas if we go to microfluidics, we are at the micrometer scale. I've got a bug that really likes the slides. And that means that we're working in femtoliters to picoliters. The volumes are really small. It is important that we keep that in mind. On the first day I showed you the concentration of some of the biomolecules. You need to make sure that actually the volumes that you're working in, you've got sufficient copies of your analytical target still present within that volume. So there.
Sometimes you
okay.
don't know.
I thought all the nasty insects were only in Australia and I was completely safe and didn't need to be scared of snakes or anything. So yeah, I'm
good friends.
We've got spiders this big at home.
Ah.
And they are my friends that eat mosquitoes. So we do biological warfare at home. I tolerate big spiders on the roof, particularly the big ones because they don't make cobwebs, so the house doesn't get dirty. But they eat all the mosquitoes and the flies. But they are, yeah, you can see the hairs. They've got big hairy legs. So we've got some impressive spiders at home. But wasps, bumblebees. We don't have a lot of wasps. In Europe there's a lot of wasps, but I'll be careful. This critter has been around in the lecture theatre. So if I hear any of you squeal, it will be that wasp. It was in here yesterday as well.
Yeah.
Unless it's a new one. So when we were just talking about the beauty of microfluidics, that we have laminar flow, and that means that we can selectively work on the differences in diffusion constants to separate different molecules. So we've got the distance that a molecule diffuses depends on its diffusion constant, which is a molecular property, as well as the time that you give it to diffuse. So diffusion constant says how fast it will go per second. You multiply it with the time and you end up with a distance. For an antibody, that's about 40 micron. For a small molecule, that's a lot larger. And then we saw that in 5 seconds, an antibody can move a lot less distance than a small molecule. And if we give a certain distance, it will take a longer time for an antibody to cross that distance or for a protein than it will do for a small molecule. We are working in the laminar flow regime, which means that we do not have all the turbulent flow swirly-whirlies around that you can see showing up in either when you see smoke being introduced into a particle-free air, or when you see water coming out of a garden hose, or when you look at a river. There's turbulent flow, there's all kinds of eddies going around. We are at the low Reynolds systems number. Typically in microfluidic systems, the Reynolds number is under 1, which is a lot smaller than being under 2000, which means that our flow is laminar. And here we can see an example of 2 blue dyes, or a green dye, a blue dye, and a red dye being introduced in a channel. They come together because we are in this laminar flow regime. They will just continue to nicely go along next to one another, and there's no mixing taking place. So what about mixing? The first thing that we could think about is just mixing by diffusion. So if we've got our 2 different reagents coming in, called A and B here, on the T junction, the flows come in, they meet, there's nowhere to go but down, so both flows just nicely form a contact line and they go down the middle. If we have a highly diffusive small molecule sitting in our liquid B and not in our liquid A, we can see that the compound from A slowly diffuses into the flow of B, which is illustrated here as the diffusion zone. And you can then wonder how far down the channel do you need to go to have this area completely diffused. So have the equal distribution of our analyte that was present in B, have that homogeneously separated across the whole channel width. If we think about how that looks like in terms of an experiment, here we've got not a T but a Y intersection, just because it's always a little bit hard for flows to go around a right corner. So if you want to have pretty images, getting a Y shape instead of a T shape always makes the pictures nicer. So here we can see that we've got a Y-shaped channel of a certain width. We've got a fluorophore coming in that only fluoresces in presence of calcium. And we've got some calcium chloride here coming in at the other channel. We can see that at the point that these two mix, that the first little bit of calcium meets the fluoro3 dye, we can see that fluorescence comes in. This is a large molecule, calcium or a larger molecule than calcium. So calcium will be diffusing a lot faster into this channel. And here you can see the diffusion of calcium, which is a little bit helped at the interface. So we can see a little bit more diffusion.
If I don't come, please take lunch.
Yeah. So we have a little bit more fluidic effect at the edges. So we've got a little bit of deviation here. But you can see in the middle, we get an increasing amount of diffusion of our calcium into the dye. And we can see a growing amount of fluorescence being formed. Here we've got the XY and XZ view. So this is looking from the top. This is looking from the side, and you can see that the zone gets wider and wider by diffusion, but it takes some time. And you can also see that it gets wider because the image here is taken, what was this time point? The different lines. So here at the beginning, we can see that we've got a relatively narrow diffusion line. The further we go down the channel, the wider that diffusive line gets. And that formed the basis of that mixing. Again, we've seen the capillary number on the Reynolds number. The Peclet number is a similar ratio, and in this Peclet number is looking at the mixing. And Peclet number looks at the convexive forces over the diffusive forces, which is the product of, again, the linear flow velocity, the length scale of the flow, which is, again, this characteristic length, which is 4 times the surface area divided by the perimeter, so that the equations apply to round channels, oval channels, square channels, triangular channels. We can also always calculate the characteristic length independent of the geometry that we make, and the diffusion constant. In a microfluidic setup, it is best to think about microns. So if we're in a large system, 10 centimeter, and we calculate the Peclet number, we end up with a Peclet number that's really large in the millions. If we do the same sums for a microchannel, we end up with a very small Peclet number, which is not surprisingly because in microfluidics we are driven by diffusion, whereas in the large scale we're driven by convection. So the Peclet number gives you a little bit of an idea where you sit on the mixing based on convection and mixing based on diffusion timescale. Low Peclet numbers, your mixing will be close to non-existent, and you will have the laminar flow as we can see here in this image. We can use the Peclet number though to understand how long our channel has to be to for mixing to be initiated. If we've got bovine serum albumin, which is a protein, it's got a diffusion constant of 70 square micron per second. If we pump that at a velocity of 50 micron per second through a microchannel, that is 100 by 100 micron. The Peclet number is 50 microns per second, multiplied by 100 micron as our characteristic length, divided by the diffusion constant is 71. This means that our characteristic time to mixing start will be 142 seconds, and the length of our microchannel that we need for this mixing to take place is 7.1 millimeter. So we need a reasonably long channel for this to start mixing. So if we looked at the H filter in the previous lecture already, where we've got a solution coming in with some solutes and an acceptor phase coming to the other side. We can use the Peclet number as well to calculate how many of the particles would actually have ended up with our extracted fraction, or if we in this instance look at BSA, bovine serum albumin, if we're looking after doing an assay for a small molecule drug, where we don't want to have any interferences from protein. Maybe we want our conditions to set up in the way that all our protein stays in our donor and then goes to waste, whereas only our small molecule drugs are being extracted. So if we work in this system with, again, a flow velocity of 50 micrometers per second, our channel is 100 by 100 micron, there is very limited diffusion of protein, of the BSA, over a time of 7.1 millimeters or 142 seconds. Whereas for a small molecule, like our acetate, the diffusion constant is 1400, Peclet number 3.6, in 7.1 seconds, or after a distance of 350 microns, we actually get significant transport of our acetate into this other channel. So if our channel is between 357 and 7.1, 350 micron and 7 millimeters long, we can have a very good separation of our extracting our acetate out of the sample phase without significant diffusion of BSA, because we are under the typical time required for BSA to diffuse to cross across this line. So we can use the Peclet number to predict which compounds are going to be crossing through the H filter and which ones are not. Another interesting application of an H filter is to look at good swimmers. So if we look at sperm and we look at in vitro fertilization, one of the processing steps that is done in the clinics is to separate the highly motile sperm cells from the ones that are not highly motile, which is pretty much separate the good swimmers from the bad swimmers. You can use an H filter for that as well, or a similar setup. So in the picture here, we've got a sperm sample being introduced. And the sperm typically is in laminar flow and therefore will be following the flow lines and get out on the other side of the microchannel. If we've got our good swimmers though, they won't be sticking to the flow lines. They will find their own way, which means that the highly motile sperm will actually end up in the acceptor phase here, because it is not only the migration, the movement of the motile sperm is not only dictated by the flow that it's in, it can swim by itself. So even though it's within the laminar flow regime, the sperm that's highly motile will swim into the acceptor phase, whereas the sperm that's not very motile is getting moved with the laminar flow to the waste. This was done, I don't have a year here, I think somewhere in around 95, and the device got implemented in IVF clinics, and then saw a presentation just before COVID, where the whole generation of the first microfluidic IVF babies was around 20 years old. So this is the use of the laminar flow in microfluidics has readily been commercialized and adopted in IVF, because it's a very easy, shear stress-free way of separating the highly motile sperm from the ones that are not very good swimmers. So the question for this lecture is, how can we mix? If we actually do want to mix, because I think a lot of the students here are doing nanoparticle, nanomaterial synthesis, a lot of you actually do like to mix, and laminar flow may be all well and good if you're a separation scientist, but you're interested in mixing. The ways that you can mix is using passive devices, where the only energy that you use is from a pump, so you use fluidics, so you can do it through injections. You can make little droplets that are interdispersed in one another, and one of the funny things that if a droplet is in a channel, it actually rotates, so a droplet by itself is a very good mixer. You can put structures in place to cause chaotic mixtures, so you put obstacles in a channel that mimic the turbulent flow, and you can use lamination. So we've got a couple of different ways that are illustrated here. The picture here is the injection of substreams. So if you have two flows, it takes really long to divide. But if you have 6 times 2 flows together, the diffusion system's distance in each of those will be the same, but the flows are closer. So if you can split the flow in a lot of parallel flows, that actually allows you to realize mixing a lot better by laminating your different flows next to one another, which could be done parallel or sequentially. So here this is sequentially periodic injection. You can have zone A, zone B, zone A, zone B, and if they are alternating quick enough, you can get mixing happening by diffusion longitudinally. There are split and recombined mixtures where you've got 2 flows sitting next to each other, are being split and then recombined under another angle. And if you go from that way, we've got a very small contact area. If we then go that way, our contact area is a lot larger, so we can have more diffusion. Then we can rotate the flows around again, split and recombine. We can have little narrow areas again to reduce the distance and therefore the time that we need to have the fusion take place. We can use high energy collision to have very high flow rates and therefore locally increase that Reynolds number. So if you've got 2 flows really come into each other heads on, we can create some energy waves and get mixing happening that way. So they are the active tools that we've got to achieve mixing over the passive one. And then we've got a range of different active ways where we can actually do something with our chip using external sources. So we can create a little stir bar. For example, a magnetic stir bar that we put in a microfluidic cell. We'll put a magnet underneath, and we've got a little stir bar that is just as an impeller mixing. We can use pressure difference with driven devices with valves or pumps. We can use magnets to move particles from A to B and drag liquid around and achieve mixing that way. We can use electric fields to mixing because we can selectively move analytes from one part to another. We can use dielectrophoresis, that we'll be talking a little bit more in detail this afternoon when we talk about the particle separations. We can use acoustic forces. Acoustic forces can also be used to move particles and move liquids around. And thermal processes increase the convection as well. The easiest way to get mixing to occur is just to change the channel length. What does channel length buy us? It buys us time. We work at a certain linear flow velocity. The longer our channel is, the longer it takes to get through this channel. We haven't done quite microfabrication yet, but there's our friend again. Hello, friend. We
Sitting here. Actually, these are 4. 1, 2 are sitting here.
Get him around our attack.
They are sitting here. 2 are sitting here. 1 is there. 4.
Okay.
I think.
We started off with 1 yesterday, so let's see how we
It's
get
4.
through the day. Maybe
I
we've
can
got.
see 4 now. 2 are sitting silently here on the projector.
Okay,
Yeah,
let's
on my
keep them
side,
there.
On my side.
Let's keep them stationary. So making a channel longer buys us time, but the problem is that we make these chips using microfabrication facilities. And typically the larger the chip, the more expensive it becomes and the harder the process. So large television screens are more expensive than smaller ones. Large chips, microfluidic chips are more expensive than shorter ones, which means that we typically go for a serpentine shape if we want to increase the channel length. Don't. So making a lot of curves means that you can have a lot of path length on a very small area. So if we have a channel that is still 100 by 100 micron and we want to pump the liquid through at about 0.1 microliters per minute for both the water and the sample that we want to mix it. Our length that we need for mixing is the velocity times characteristic length over the diffusion, which equates the Becquerel number times the characteristic length. So our velocity is 2 times the volumetric flow rate divided by our characteristic length, divided by our surface area, is in this instance our flow rate of 0.1 microliters per minute, comes down to 3.3 times 10 to the minus 4 meter per second. So we convert the the volumetric flow rate into a velocity, into a linear flow rate. So we go from microliters per minute to meters per second. So we go from volume per time to distance per time. If we look at acetate, the characteristic length required for mixing acetate is 2.4 millimeters. The time to do that is 7.1 seconds. If we look at BSA, we need 50 millimeters to mix from one side to another. If we then say that our serpentine is on a square with half of it covered with a channel, then that's the area that the microchannels take, and then we can calculate how many of the zigzaggy turns we need. So this is one turn, this is the other turn. We can calculate what the length is and therefore how many turns we need to realize the channel length that we need to mixing to take place. And that will then be taking place in about 140 seconds. So if we've got a channel that's got 7 zigzaggy things going up and down, then in 140 seconds we will have BSA being mixed in our channel. So for mixing acetate, we need a short channel and a short length. If we make this channel a lot longer by having 7.5 turns, it takes 140 seconds from going from this intersection here to the outlet and will be mixed there. So the other option than adding turns and turns is to do parallel lamination. So to have, instead of having one interface, you can have multiple interface. Where was my 47? So if you can calculate from that perspective, if you want to mix in a certain time, how many layers you want to have. So, did I do the calculations here? Did this last night. So if you've got n different layers, then the time that you need, so number of different slices sandwiched, then you need 1/n less time. So if you've got one layer, then you've got one amount of time.
Why do you increase the channel length in zigzag motion, not in linear motion? Linear.
You can do either. So this is adding it laminar channels in the length of the channel. You can also chop them in space that way, but that needs a higher level of fluidic control. So it is lamination lengthwise you can easily control using your fluidic structure. If you want to do segmented flow, splitting up vertically, then being put on its side before it's being merged back again. So we've got two channels come in, they are split vertically, rotated around and being folded back together. So at the first stage of the split and recombine mixture, we've got our dye coming in with our solution, and we've got one single interface as we just spoke about. After having gone through one of these mixing units, the flow gets halved, so we've got a wasp. We've got two different flows now that are both half the height of having a dye and an empty face sitting next to each other. If these then, by having the channels geometry being put on its side, and again laminar flow allows us to do that, we can put these two on the side and we can see that at this stage we have 1, 2, 3, 4 interfaces where the fusion can take place for the mixing. We can then go through another operator, so we chop this one in 2 different layers. Here we've got dye, no dye, dye, no dye. On the top half, we also have got dye, no dye, dye, no dye on the bottom. We can then put them up straight and put them back together. And now we have 1, 2, 3, 4, 5, 6, 7, 8 different interfaces where our mixing can take place. So you can see that with the sequential lamination, where we get all the flows taking place, we can get very efficient mixing taking place. So the mixing can be done across the 3 dimensions. Then we have also a range of features if we want to do mixing to kind of try to mimic the turbulent flow profiles using fluidic structures. And that is pretty much just pestering the flow. So we've got our solute and our solvent coming in. And you can see here that there is no easy straight flow path anymore, but the liquid has to go around the corner and then a sharp corner again, and it hits a wall again. And that creates little eddies, little swirly whirlies at the corner. And it's those swirly whirlies that then allow you, even though you are still under laminar flow conditions, to have convective mixing, because you get little flow areas at each of these corners that will get the mixing to take place. Another way to achieve that is just to put a lot of pillars in place, or a porous material, because then again it's not as controlled as a split and recombine mixture, but these pillars here will create both. It will split the flow and recombine, because the flow will have to go around the pillars, and that way you increase the surface area where your solute and your solvent are forced in contact, and you will be able to get mixes taking place. And here we have a channel that just goes into a lot of different directions, again relying on the fact that we get differences in flow velocity between the long and the short corner, causing these circulatory flows at each of the angles. And they start working like little stir bars to get mixing to take place. So this one is more efficient than this one, but if you get your channel to do weird enough zigzags, you can enhance the mixing compared to a diffusion only different process as well. If we go to intermediate Reynolds numbers, you can see that the things people have come up with are increasingly complex. So here there's droplet-like features where part of the flow needs to go back in each of the mixing stages. Here we've got the flow, it goes up, left, down. So again, we rely on all these eddies at the corners. This one, they're all variations of the same theme, and typically these designs arise from computational fluid dynamics. So there is software packages like ANSYS and COMSOL, and there you can put some obstacles in and see what your flow lines do. And if you can see that your flow lines get large eddies, large circulatory parts, that is where you can get good mixers. So a lot of these designs were thought like what's happened there. Then the length and the width have been optimized using thermodynamics, fluid dynamics, and then you can see if you can make the devices and evaluate the quality of the mixing. This is one of my favorites because they're relatively easy to make. It is putting some traffic humps on place. So you only need to put some lines. If you put some little angled features on the bottom, it is very much like driving your car across a traffic hump. Everything in the car moves, particularly when you walk too fast. So if you've got a high flow, you've got laminar flow happening, but you put a traffic hump on the middle of your channel, everything will have to move up, compress and mix, and that creates a lot of diffusion. So these are referred to as the herringbone mixer, where you get a change of flow because the flow hits an obstacle and it will start getting a circulatory motion happening in place, which is what is happening here. So you can see here the traffic humps are not only straight, they've got a straight corner. And that is to try to redirect the flow and then go up the wall and try to get a circulatory motion. Here from the inlet we can see the die and our buffer coming in. You can see little effect at the first one, at the short end, because it doesn't quite redirect the flow yet. But here we can see that the traffic humps actually get a flow happening during the surface, and you can see that the mixing, the change of that flow pushes the die further to the center of the channel. Then they go the other direction again, but the flow still pushes this further and further. And you can see that every time that we go from a short arm to a long arm, we get more of that rotationary flow being happening. And that means that our mixing here, if you look at this distance, our mixing is a lot more efficient than it was when we would just have had laminar flow here. Because here you can see on this distance really nothing has happened yet. So we would have still have no mixing at all without the features. But with these herringbone structures on the place, we actually can get a different flow motion that promotes the mixing between our solvent and our solute. So there are a couple of different ways to work with fluidic structures, with fluidic design. There are also ways that we can actively mix using pumps and valves, where if we get a pulse of solvent and a pulse of our analyte to come together into a microchannel, we get that segmentation happening sequentially. And we can mix that way because our diffusion, if the droplets, the segments are small enough, we can anticipate that mixing will be working that way. We can achieve the same thing when we've got our solute and our solvent coming in, but we apply little teasing pulses using a pump from the side, where we just push the liquid to one side of the channel and then to the other. Again, pretty much getting the idea of a gyro rocker, but then organized within the microchannel. This in here is the little stir bar. So if you've got a magnetic element, you put a magnet underneath, you can get mixing to take place that way. You can use the electroosmotic flow and then have an AC voltage. If you have changed your polarity, your electroosmotic flow goes the other direction. So here we've got electroosmotic flow pushing one way, pushing the other way, achieving mixing that way. And here we've got, again, AC voltages to create pressure waves in one direction, causing pressure disturbances. So if we all of a sudden have a large expansion of our channel, we get change in pressure because the pressure is divided by the channel width. If we all of a sudden have an expansion, we get a pressure drop, which again results in these eddies, the recirculatory flows, which pushes your liquid out and in and enhances that mixing. Electrokinetic fields, and the last one here was using temperature. So if you use the temperature of one of your solutes and not the other, you change the viscosities, and you can use your change in viscosity there to affect the mixing. Sound waves are very good. We're working at a small scale, and small particles can be moved by sound. You realize that if there's a festival, or even if you get close to the speaker of your mobile phone, sound is a physical vibration. And the force of this vibration is enough to enact movements inside the microchannels. So if we've got a PDMS microchannel here, with a piezo transducer, which is not much more than the little membrane. I'm not sure if you've ever dismantled a little speaker, but there's a little vibrating thing in a portable speaker. as well as in your phone. So that's the piezo transducer that's sitting here. If you have a little bubble sitting in one of these cavities and you start applying some sound waves, which could be the acoustic waves, so it could be just sound, you get little vortices happening at this bubble because the transmission of the sound through the gas bubble is different to that in the material, which means that the bubbles are sitting here all at the corners, and we'll learn later PDMS is a hydrophobic material, so bubbles really love to stick to PDMS. So in this device, little bubbles are sitting here at all the cavities, and each of these bubbles at these tips creates a little eddy once the sound is switched on. And again, those eddies will allow you to mixing. So using a sound field, using an acoustic wave, you can mix reagents by creating these force fields. Light can help in inducing heat, or in this case it's particles. So here we've got two different oil phase and a water phase which has a photosensitive material in there. If we apply the pulse of light, it means that this photosensitive aqueous phase becomes a particle. This particle will start bouncing around based on the pressure differences in the cavities, and there with that start dragging the other liquid around. So they become pretty much helpers and little stir bars because of these expansion and contraction areas. So if we've got our two oil phases separated by the thin film of photosensitive dye without any light being applied, everything is liquid, we have laminar flow and not much happens. We'll have a little bit of disturbance, but the geometries here are selected that we don't get too much mixing. However, if we polymerize this into little beads, the beads will start following the flow lines a lot better. And you can see here that these beads start taking the circulatory flow patterns that are happening, and you get a high level of mixing coming out. So you can have your flows going continuously. Nothing happens if your photoactive compound is still a liquid. If you make little particles here from your phase, then these droplets, these particles will start making the mixing. Another way of doing mixing is that people create cilia. How many biologists do we have here? From biologists. So what are cilia?
Not biologists, but understand.
Yeah, so what are cilia?
These are the small hairline structures outside the body of amoeba or paramecium. These are single cell organisms.
Yeah, so they're single cell organisms, but there's also cilia in our lungs. So
Yeah.
our lungs are covered by a mucus layer, but we don't want our lungs to be full of slime and liquid, because then we can't have air transport anymore. It's getting interesting. So the surfaces of our airways are coated, have little cilia in there. And they are little pillar-like structures that continue up. So our lungs like to have a clean layer of mucus in there, but there's the cilia that are moving, pumping the slime back up so that we can swallow it and get it into our intestines, and our lungs get continuously refreshed. So a lot of biological systems have these wavy structures, viscous liquids. Some very clever people thought that we could use that in microfluidics as well. So they started making little pillars, introducing some of them a small magnet on the top, and then you can microfabricated cilia. You move a magnet underneath, you can get the cilia to do the same movement as that the cilia in our body do. It's up. So device here with a column here of the cilia. Here you can see them on an SEM in PDMS. So they're just a little circular pillar, and the tip of that pillar. Creating these cilia you can get from a non-mixed condition to a properly mixed condition by just having them move up and down. So here you can see the way that it works. So there's magnetic, 4 different electromagnets. If you get fields, you get the cilia to move one direction, and you can get them to flop in the other direction. Another way of getting cilia to work is using light. So if you make the cilia not out of one polymer, but out of 2 different polymers, you can get, depending on the light, you can get the polymer to either stand straight up or like a bimetal move around. If you make the cilia like a bimetal, where the materials respond differently to an electric field, you can apply a potential difference and you get the cilia to either stand up or fall back down and get them to move that way. The last way of realizing actuation is making them kind of inflatable. So if your cilia are hollow tubes and when they're and you apply a pressure difference, get them to curve around with the flow. If they're not actuated, because they go with the flow, if you apply pressure, they become a lot stiffer and you get them to stand up. So you can pneumatically get your cilia to either stand up or go with the flow. And by actuating that between the standing up and the being folded over, you can get them to move and help as a mixer. So there's a whole big toolbox of how you can get different parts to mix. And if you design that a device, there are a couple of different decisions that you can make, and as we've already seen with the sequential mixing or the parallel, there is not really a right or wrong. There's just a large toolbox, and some solutions will be better to some applications. So the big choices that we have is that we've got active mixers where we need an external force, which could be a magnetic field, it could be sound, it could be an electric field, it could be the actuation of the cilia. But in active mixing, we have something that we need to control to get the movement in motion. Before that, we talked about the passive mixing systems, where we use the fluidic design to enhance the mixing, which could be either by increasing the amount of surface area and therefore decreasing the diffusion time required for full mixing. That's your split and recombine mixing. Or you create expansion contraction channels where you create eddies on the surfaces and get your liquids to have more circulatory flow and therefore mix better that way. Or we have the structures implemented on the bottom, like the herringbone mixer, that instead of having laminar flow, we start getting the flow to kind of go around in the channel, that way enhancing mixing. So the choice is very much, typically the active mixers are a lot more faster than the passive mixer, but it complicates your instrument design. So it depends on your application need, if you need to achieve mixing, if you're happy to just get to a serpentine channel and increase length, if you want to get a passive mixer by using some design elements, or if you want to go for an active mixer, make your instrument a little bit more compact, but still know that you've got a simple chip and very fast mixing. So there is no good or bad, but this provides a little bit of an overview on how you can realize mixing in the microchannels. Which brings us to lunch, if there's no further questions. So yeah, some of the mornings. So I think some of the days we have a 2-hour lecture in this block, and some of the days it's a 1 hour. So we're finished a little bit earlier than the other days, but I think we can just take a little bit of a longer lunch break. Any questions?
Seems quite complicated when it works. Come to a practical.
It is very much a toolbox.
Yeah.
So there is have two types of scholarships. Ones are just academic merit. So if you have very high scores in your undergrad, your master's thesis is well ranked, then you may be able to just apply for competitive scholarship based on your own performance. And we have scholarships that are attached projects. So if I've got project funding, I may have funding for a PhD student at the moment. I'm looking for someone to develop a fluorescence detector. So I need someone that can engineer and understands optics. So at that point, it's not necessarily the person with the best grades, but it is someone that has got the skills in the area that I need. So it's then finding a match in skill set. So students that have developed here, and I get the CV, then we'll do an interview, and then there's a direct offer option. So we've got two different ways. One is the student comes first, and then we look for a project for the students. And the other version, the project comes first, and we look for the best possible person for the project.
So in your master's program, it is 2-year program masters? Means after
So we've got a master's by coursework and a master's by research. And I think the coursework master's is 1 year, the other with the research
coursework masters means no work.
No, or very small. So there will be a part of a term will be a small research project.
Okay.
But research masters, there will be a 9-month project.
Okay,
So there will be a research project in addition to the coursework.
So in these 9 months, he's not studying in class. He's only devoted to the research.
Minimal classwork. So we sometimes there is, like if someone would be doing analytical chemistry, there may be a course on mass spectrometry or spectrometric methods.
Okay.
Or there may be a course on academic writing.
Okay. That's
So it is not research only. There may be a couple of weeks where there are some courses that are targeted at the postgrad level, but the main focus of the year will be the.
So when we say on the basis of merit, because when you say marks, the score that is scored by a student in India in one university, different university will have a great variation.
So we've got an office that have got all kinds of tables how things translate.
Okay.
So there is a complex ranking process of all those applicants.
Is there any test or something like that you can take? So
There is no test to take, so it is only on the information that we get supplied with.
Student is applying to each university, or it is applying to a certain place?
To each university, and may even get multiple advisors at the same university to try to support them.
For PhD, for master's course?
For master's course, you just apply at the university if you meet, I think, the English language requirements and.
Which is that English language requirement is TOEFL or
Yeah.
IELTS?
Either or.
Either.
Yeah. So the
IELTS score.
Yeah.
And then the score for then mark sheets.
Yeah.
Then it is graded by the university. If it is okay, they send an offer letter and then the student apply for the.
Yeah, and then the barrier is not as high because at that point, so the number of PhD students is limited because they get a scholarship.
Yes.
The masters don't get a scholarship.
Yes, that's.
So it's then if we think there's a reasonable chance of passing, they can enroll.
That way also the student gets into a place, do a masters, and then he realizes what type of work is going on, and then he can choose work of his choice, rather than just getting what he's getting.
So that's exactly what the guy that will get married in 2 weeks' time has done. So he did his undergrad in India, then paid for a master's by research at Deakin University, did his research project. It's all working?
We are
I'm ready then as well. Let's get going. So we'll be talking about particle and cell separation. And particles, we can take that pretty broadly. So a particle could be a biological particle, a cell, could be bacteria, could be plant cells, animal cells, fungi. Could also be a virus. We all now know the COVID virus looks like as a particle with spikes. You can also lyse cells into their different organelles. They could also be considered particles. And biological particles and the non-biological ones come in a whole range of different sizes. I've got my pointer here. So if you look at animal cells, they're typically 20 microns. Depends a little bit on the size. So your epithelial, endothelial cells are around 20 micron. Your red blood cells, I think they're little 5 micron circles. Your white blood cells are around 50 microns. So it depends a little bit on the cell type, how big they are, which makes understanding a little bit of biology, if you want to develop a separation method for a cell, important, because whereas we originally think that cells may be represented by nice spheres, they're nowhere near that. Blood cells, for example, are little discs. So they're circular if you look at them now from the front. If you look from the side, they're actually flat. So they're like a little, almost a frisbee. Then we've got the different organelles here that are smaller than a micron. Bacteria are kind of a couple of micron big, depending on what they are. So you, under the microscope, you can just see them. And then viruses have a broad range in sizes from 10 to 1,000 nanometers. So it depends really on the virus, what you're talking about. Not quite a bioparticle, but certainly an analyte class of increasing concern are microplastics. And if the microplastics break down, then we end up in nanoplastics. So we, in analytical chemistry, it's increasingly known and understood that bits of plastic are found anywhere in Antarctica. And that becomes a challenge that may have some microfluidic solutions trying to concentrate and isolate the plastic particles to then be able to characterize them and what they're actually doing. Because there's a lot of risks. Plastic as themselves are not healthy, but the micro and nanoplastics by themselves are very good sorbent. So they may actually be absorbing toxins from the environment and pre-concentrate them. So we'll have Professor Malik's lecture on pre-concentration solid phase extraction after this. If we put stationary phases all around them and we then put them in our food, we may actually start eating a lot more toxins than we normally would do. So why would we need to play around with particles? Sometimes we want to know something about the particles, sometimes we just want to get rid of them in order to do separation. So if we want to do water evaluations, the particles, or if you have any idea what urban wastewater or plastic load is, isolate just the microplastics. A lot of diagnostics we can see on blood. Sometimes we just want to get plasma because we want to know the dissolved molecules in there. The blood cells are just in the way. Sometimes there could be a disease with the blood cells themselves, so we want to get rid of as much of the liquid and isolate either the white or the red blood cells depending on what we're looking at. Very big application area are the circulating tumor cells. Anyone heard of them? If we've got a tumor in our body, then this tumor may be, particularly if it's metastatic, it may be shedding cells. So that may mean that the tumor is not only sitting in the lungs, but small clumps and single cells of the tumor break off and they end up in the blood circulation. So even if you don't know that you've got cancer or where the cancer is, these cancer cells may already be circulating in your blood, which means that if you find a way to extract these circulating tumor cells from the blood, you may get an alert a lot earlier that you've got cancer than you would otherwise have, because cancer is a silent disease. It may be developing for a very long time before you actually get sick. Last application where bioparticle manipulation is really important is in bioreactors. Bioreactors are used in biotechnology, but also increasingly in cancer therapy. So there's the CAR T cells that are used to help use the human's own immune system to fight a cancer. we do want to raise certain cells, but we at the same time want to be able to exchange media and remove bacteria. So if we can, in a bioreactor, replace the fluid around the cells without disturbing them, we can actually get rid of waste products and give the cells fresh and new nutrients. At the same time, if we can separate the small particles, we can remember here, the cells are around 20 micron, bacteria are around 1 micron. There's a significant size difference. So if we make a separation from anything that's smaller than 2 micron or everything that's bigger than 2 micron, we can get rid of a lot of the bacteria whilst we keep our human cells. So size there becomes a way to resolve, to separate two different cell types where one may be desired and the other one may be considered a pest. Particle separation is not new, it is not something from microfluidics. I don't have it with me now, but I like my coffee made from some ground coffee with a filter. So I've got a little hiking coffee maker with me, which has got a little metal mesh to keep the coffee grinds up. I pour boiling water in my little cup, drip in my little container that contains my coffee grounds. This metal mesh there prevents the coffee grounds from up in my coffee, but the coffee can still brew itself and I can extract my lovely caffeinated drink into my cup without getting all the grounds in my mouth. In the lab, sometimes we go a bit more advanced in a filter. We may have a centrifuge. In a centrifuge, particles with a higher density will move to the bottom. If they are smaller, we can centrifuge at a higher, like in an ultracentrifuge. It's a really effective way of separating different particles. Problem, however, is that if you want to use a centrifuge, you need to prepare the test tubes, you need to balance the tubes in the centrifuge, you do your run, and you then need to manually separate your supernatant from your centrifugate at the bottom. Which means that you need well-trained staff, and therefore the assay becomes more lengthy and is not as easy to be implemented in the field. Same thing, filtration can be really good. There's the little syringe filters. My coffee filter works fine because my coffee ground is all relatively coarse. But if you've got fine particles, your filters may get blocked. Another problem with filters, particularly for extended period of time, is that biomaterial protein may start fouling your surface. So are there also fluidic ways, membrane-free ways of separating particles? And our friends the biologists have different ways. So that where cells stain cells with fluorophores, there is fluorescence green, then a little liquid pulse supply is ordered into a separate vial because the interest were after. Activated the fluorophore bit, this magnetic the other, allowing for the different separation of cells using a magnet. The current lecture will be about how microfluidic methods can be used for particle separation. Microfluidics, as we know, deals with the behavior and control of fluids and particles at a sub-millimeter scale. And we've got advantages in terms of low cost, fewer reagents, and the ability to integrate multiple processes and automate them. Like we spoke this morning about the mixing, we have again a toolbox here. So there's no direct winners or losers. There's horses for courses. If you want to win the Formula 1, you probably don't want to do it in a Toyota. If you want to drive from here to Patiala, a Toyota will do the job. So is a Toyota a good car or a bad car? Really depends on the situation. And the same thing counts for the mixing methods that we discussed this morning, and here about the microfluidic separation methods. So we've got, like we had active and passive mixing methods this morning, we continue to use the same kind of language. What was active this morning? When was something an active mixing method?
Inputting some energy from outside.
Exactly.
In order to achieve the
So all our active...
plastic waves and...
Yeah. So here it's exactly the same thing. If we have an active separation method, that means that we need to put in an additional energy, which could be an electric field, it could be a magnetic force, it could be, again, you're already right there, the acoustic forces. The passive separation methods, there we don't do anything but provide a pump to provide the liquid flow, and we use the forces on the particles in the fluid to achieve the separations, which unfortunately comes accompanied with a range of equations again. So I'll try to be light on the equation, just so you show with some errors how the different particles can move, and see it if you need particle separation. There's reviews that compare one better. Dielectrophoresis, which is an active method, which gives an additional force. In dielectrophoresis, that's an electric field, but in contrast, where in electrophoresis, where we had a continuous electric field, a DC field applied across with electrodes, or if we've got a DC field and we've got an equal size electrodes, the particle is pulled as much to the right as it is to the left, and we've got no real net effect on the particle. If we get an asymmetrical field, however, we get more pull from the higher intensity field near the small electrode than at the large one, which means that the force will start depending, different particles will experience different force in dielectrophoresis, which means we will be able to use dielectrophoresis to separate particles with different properties. The strength of the force that we can achieve with dielectrophoresis include the electrical properties of both the medium and the particle. So it is the difference of the properties of your particle with the medium that the result if you've got positive or negative electrophoresis that you move away. So in this instance, we've got an electric by having two interdigitated electrodes. So we've got the field here is applied at offset electrode with asymmetric fields, and we've got particles that are pulled close by. Some of them are moved, which means that we can send some. By the time we can control where the particles go, it also means that we can use it in continuous flow situations. So if we look at a flow through microchannel here, where we've got a clean buffer medium being flown in the middle. We've got cells being injected from both sides. We still have laminar flow, so our buffer and our cells suspensions are happily flowing alongside each other. We have electrodes sitting here on the top and bottom of the channel, where we can do dielectrophoresis with. The dielectrophoretic forces, however, give a driving force away from the electrode. So negative is the particles that we've got in the cells here are being pushed away by the way that the system was set up. So now we've got two different forces acting on our cell. We've got the hydrodynamic force, because we've got our liquids all going into our channel, and we've got flow happening here going towards the waste channels. That hydrodynamic flow is, except for the zero flow at the wall and the parabolic flow profile, that hydrodynamic force is pretty much the same across the bulk fluid. But this dielectrophoretic force drags the cells down depending on the angle. which means that a particle that or a cell that was in the mixture here is being pushed in this direction by the dielectric field, which means here you can see the cells that are being pushed by the dielectrophoresis away from the electrodes into the central collection channel. This now means that we can extract our cells from the cell mixtures applied to the outer flows into the clean buffer medium, where we can collect a concentrated clean sample flow by applying the AC potentials to the arrays of electrodes that are positioned here over the channel. As we've already seen with Professor Baga yesterday, that if you can concentrate things with isotechophoresis, you don't get good resolution, but you then get good resolution with the zone electrophoresis. If you stick them together like two Lego blocks, you may be able to get the best of both worlds. A lot of people in microfluidics are engineers. Engineers love Lego, so they like combining yellow and blue blocks. That's exactly what they've done here. They developed dielectrophoresis, two different dielectrophoresis devices. One to focus all the cells slowly in on one side. You can see a cell suspension coming in, all cells coming in kind of random, but then ending up very nicely lined up in the first. So the dielectrophoresis here is aimed to just put all the cells together. Then the settings were done slightly differently at the other side. Where's my? I think my laser is near dead. I've got a tiny green point, but I can't see it on the screen anymore. I'll use the one here. So you can just still see it on your hands, but not on the wall anymore. So here we have relatively strong dielectrophoretic. Are you wanna? Let's get back one slide again. That's there we go. So here we're using dielectric field to get all the particles together. Then here we use the slightly different intensity where the fast moving particles are being transported across. Slower ones are being deviated.
You can use it like pencil, so you can draw with this one.
Yeah. So you can see here in the second stage are fast moving particles. The large ones move very quickly in the dielectric field and end up in this outlet. The smaller ones that were also focused here take a little bit more time. But this section in here was taken short enough. Thank you. This section in here was made short enough that these red particles, the small ones, they move from the side to nearly the middle, but not far enough to end up in the other collection channel. So here we can see we've got a mixture coming in. First dielectrophoresis step, all the particles are lined up. No matter if you're big or small, they all get swiped together. Then we have a short section where we apply a force that is stronger on the larger particles than on the smaller ones. We pull all the large particles out so that they end up on the right hand side of the channel and end up leaving the channel on the right hand side. Whereas the smaller particles, they don't experience as much force and therefore they move slower. If I kick a ball, it doesn't move really quickly because I'm not good at soccer. Jetty maybe is a much better soccer player, so if we both hit a ball, they will start rolling at different rates. If we have a certain distance to cross, the ball that I kicked is not going to make it and stays in the bottom channel. The one that Jetty kicked may have made a line and goes away. So based on the velocity developed here by dielectrophoresis, we can separate the large particles from the first particles.
Common for used.
Yeah, so this is all done in PBS. So the electrical permittivity of the buffer is typically adjusted to match the electrical permittivity of the samples. But this is typically applied for the separation of cells. And cells are typically not happy if you do anything but phosphate buffered saline. So that was dielectrophoresis using an asymmetric electric field. The next one to look at is magnetophoresis. Phoresis, we've heard it come by a couple of times, is movement. Magnetophoresis is movement activated by a magnet. If we manage to magnetically activate our targets, we can selectively pull them out of a mixture. So it's either using working in a ferrofluid that's magnetic and then have different forces in the fluid on large and small particles. In the ferrofluid we've got the liquid is magnetic, or we can do it in under this is just in the ferrofluid. So we have a mixture of particles coming in. If we are in deionized water, then we get a little bit hydrodynamic separation, but we still get mixtures going either way. If we work in a ferrofluid, then we can get different. At that point, we can pull the larger particles that have a high velocity towards the magnet, whereas the particles that are not impacted by the magnetic field will be leaving the channel through the other. If we talk not in a ferrofluid but active magnetophoresis, then we have different cells that are labeled with magnetic particles. And here we can see that here the circulating tumor cells have been labeled with a magnetic particle. We've got a blood sample that's got the red blood cells, the white blood cells, and the circulating tumor cells. Circulating tumor cells typically have specific antibodies sitting on their outside where you can covalently attach a magnetic B2. If you then have a magnetic field applied over this channel, the magnetically labeled cells, in this case the circulating tumor cells, will be migrating in the magnetic field, whereas none of the other cells have the label attached. They don't experience the magnetic field, and they just go from the blood to the waste reservoir. If we then have an impedance electrode sitting there, then we can measure that a cell is coming by, after which we can selectively collect the circulating tumor cells into a vial for later analysis. As you can see here, and I think this video here, I need to switch the laser off. So this is a setup where magnetic cell sorter works. So you can see going by in a microchannel. But I think what's more interesting is to see how many setups in microfluidics actually take a whole space, because that's the meter-long tube that's attached to the microfluidic device that is moving to cell comes from. Acoustic fields can also be used to focus particles in the nodes where the waves get together. So here we've got an example where the field is adjusted so that the red blood cells focus in one direction. In a standing wave, we get these actuations. We've got waves, 2D waves that get really complex, and I particularly like this movie that actually shows how you can use acoustic fields, how you can use sound to distribute particles in different ways. So they increase the complexity of the acoustic field here, and you see how the different nodes where the particles concentrate change depending on the complexity of the acoustic field that's being applied. So let's start off now. It's just some salt, so just some salt granules that I used. So just a speaker is being attached, and the higher frequency. So you can see the forms being by the acoustic fields, the particles, the notes are taking place at different orientation, and you can just see that by the vibration of the field, the particles actually want to sit in the nodes, in the valleys where they experience the smallest amount of energy. So the higher the frequency goes, the more complex that gets, and the more complex patterns. This again, I won't go through all the equations, but this is all physically explicable. So you can predict based on your material properties and your fluidic properties where the nodes in your microchannel will be, and therefore you can follow two different acoustic favors, so you can get little columns created. Here we've got a linear field where we can get all the particles to just sit together in lines. If you start being able to play with different acoustic field generators, you can start getting your particles to act in terms of letters. So you can make temporary structures from particles. I've seen people using it as a sieve, so they get particles to align as kind of a grid. Using it as a sieve, if it tends to be blocked, you just let the acoustic field go, which means that your blockage disappears because your barrier disappears. And then you put acoustic field on again, and you have a new fresh filter. But it can also be used for longitudinal separations, where you can focus the particles towards a central outlet channel using, so again, two different stages. One is to put all the particles roughly into the central zone. In the second stage, one set of particles is pulled towards the middle and goes into the outer outlet, whereas the smaller particles, in this case, we're looking at sepsis. So the bacteria were pulled here to the middle, whereas the blood cells go to the outside, and then the collection from reservoir 2 was then later processed by PCR to see what the bacteria were that were using the sepsis. Another part of, so moving into passive displacement version. So acoustic waves, dielectrophoresis, magnetophoresis, all used in external fields. The first passive technique I want to look at is deterministic lateral displacement, which I feel feels a little bit like size exclusion chromatography. So what we have is that we've got pillars that are slightly offset in a microchannel with a certain spacing apart. If we've got a mixture of particles coming in, the small particles actually notice very little of the pillars. So they come in, it's laminar flow, they just go straight and they go to the bottom outlet. The big particles, they actually bump into the pillars and therefore they are deflected. Because the particles are not put in a straight array, but this array is under a slight angle, so you can see that this one is not lined up but it's slightly higher. That means that if the large particles bump to one, they're more likely to end up with upwards deflection than with a downwards, which means that this one gets an upwards trajectory, and ultimately after a very long period, because we can see an interruption here, so this is a much longer channel than it looks here, our large particles will be going out through the outlet, our small ones will be non-deflected and going down. So we can use an array of pillars to bump big particles to go to the top outlet, whereas our small particles will be moving in a straight direction.
What is bumping? Movement or?
Movement. So we've got a flow of liquids that's containing our different particle sizes coming in.
That is driving force.
The driving force is if you collide with a particle, you get impact. So you change, if I bump into this table, I change direction.
Yes, definitely.
If I would be 10 sizes smaller, I didn't have to bump because I'd fit straight through, so I'm not deflected.
These holes are vibrating.
No, it's just pure on impact. So these pillars are sitting there,
Okay.
and the big pillars hit particles more often than the small particles, just because of their bulk size. A scooter is easier to navigate in traffic than a car.
But how that is separating these two?
Because these are not in a straight line, these are slightly offset.
Okay.
So the likelihood that you get bumped up is higher than the effect that you get bumped down. So stochastically, there will be a number of times that they get a little downward motion, but over 1,000 pillars, the net effect is that they get bumped up more often to the top. This is just happening in so the chip bottom sits on the table and the pillars stick out vertically in the Z direction. Then we go to the passive techniques that use the different forces on the particles that are there in the fluid. And in the simplest forms, I will go through 2 or 3 iterations. Again, if you need one, you can do the maths all the way in detail. At this stage, I just want you to be aware that there are, because we work in a small channel, we have different forces, we can use that for particle separation. So there will be a few equations in there, but look at the overall effect. So we all know that we have a parabolic flow profile if we're flowing a liquid through a tube. Which means that if I'm a particle sitting in this lane, I'm going slower than the particle sitting here. The fluid around me on this side is moving slower than the fluid that's sitting next to me on the bottom side. This creates a shear gradient lift force. It's a lift force that pushes the particle away to the side where there is the lower velocity. At the same time, our walls give a lift force as well, but that goes in the other direction. So we've got the FLW going towards the channel. So yes, we've got the shear lift force is going one direction, the lift wall force is going the other direction, which means that every particle, depending on where it sits, it feels forces in 2 different directions, and it will find an equilibrium point. And these equilibrium points could be in a circular channel, they're radial. There's typically 4 nodes in a square channel, and if we go in rectangular channels, there's a few more nodes where particles will be agglomerating, because it's the minimum difference between the lift force that comes from the shear gradient and the lift force that comes from the wall effects. So these only work at higher Reynolds numbers. So if we work at low Reynolds numbers, so relatively low flow, you can see that nothing happens here with the blood cells, and we've got quite a homogeneous distribution, because the wall and the lift forces are not that high. The higher our flow rate becomes, the more steep our parabolic flow profile, the more pronounced these forces become. And here you can say if we increase to Reynolds number of 50, 100 and 150, you can see that the blood cells here start focusing in these nodes at either end. So this is looking at the either end of the channel. We have our 2 energy points where the cells have an equilibrium of force.
Can you go to previous slide? Were not we saying that this parabolic flow is not happening in the microfluids?
It is also happening in the microfluids, but it doesn't happen if you use an electric field. So if you use hydrodynamic flow, you always have a parabolic flow because you push the liquid through, and the velocity of the wall will be 0. If we've got the electroosmotic flow, we generate the pump at the wall with the charge. Okay. So this type of separation would not work under electric osmotic flow conditions. It needs the parabolic flow profile to get the shear forces. What they then looked at in this article is look at the behavior. So we just looked at normal blood cells. They then found that if you have expansion and contraction channels, that the circulating tumor cells that are stiffer and larger tend to focus on the middle part of the section. So here we've got the circulating the abnormal cells. And you can see that here they stay in the middle of the device between the contraptions, whereas the other cells, they accumulate towards the sides, because the circulating tumor cells, they're larger, they're bulkier. The experience is the ideal node where they sit is different. So here is the example of the device being used. So we get a mixture looking from the top and from the side coming in, where our blood cells are distributing at the sides, but our tumor cells are focusing in the middle. So we've got our blood cells sitting in our two tracks at the sides. Our tumor cells are focused in the middle and are focused there more intensely because we've got the expansion contraption channels, which means that at the end of the extraction contraption channels, we can actually have all our circulating tumor cells coming out of one outlet and get our blood cells to come out of the other outlet. So we can extract the circulating tumor cells from a relatively large volume into a smaller volume, because these they will be sticking to the center flow lines, whereas the smaller blood cells will be in the extension traps and do the focusing sitting on the walls. So we've got large cells that are circulating tumor cells focusing in the middle, small blood cells sitting on the outside. We can then have different collection containers and that way isolate the circulating tumor cells. The movie is not that interesting. Another part of using different forces on particles is the microhydrocyclone, which anyone knows a Dyson vacuum cleaner? The way that the hydrocyclone works is very similar to a Dyson vacuum cleaner. So we have a feed of particles coming into a microchannel that is tapered. We have two different forces on our particles. We've got the centrifugal force, which is an outward force on the particle. And we've got the buoyant force, which is a function of the density difference between the fluid and the particle. And that buoyant force that is moving to the inside. And then we've got a drag force there that is just opposing any movement. It's a little bit of a teenager. But what happens here is that if we've got a large particle, it will be pushed because it's fed by the centrifugal force to the outer wall, where we've got a flow going down and the particle leaves the system through the underflow. Whereas the light particles, they're the buoyant force going to the inside is larger because they're not pushed as much to the outside. So the small particles end up in the central flow, in the hydrocyclone, and leave the device through the overflow. So we've got two different liquids coming out of, so we've got a mixture coming in as the feed. The flow swirls around in the hydrocyclone. The fat, heavy particles move to the outside and leave through the bottom. The little particles are sucked to the middle and leave through the top. And that way we can separate different cell types, or we can separate sand and particulate matter from a clean sample to do later analysis with. And this paper is quite interesting because the Majid Warkiana that realized that we could also do this on the micro scale was kind enough to put all the STL files for 3D printing the hydrocyclone on there as well. So you can, if you get a 3D printing, you can just get the designs, get your printer to make one, and then see how it works on particle separation. Also working on forces happening in a spiral field are these spiral devices, where we've got a sample being injected from a central inlet and spiraling around. Then again, we've got forces pushing the particles to the outer wall, and we've got forces dragging it inside. So we've got Dean forces here going in opposite directions. We've got a flow going, the Dean vortex is going here positive, here it's going negative, and we've got different stable positions for different particle sizes. If we adjust our flow big enough, flow conditions well enough, and that always takes some experimental trial and error, we can actually organize life so that big particles go to the inner wall, small particles go to the outer wall, and we can collect the small and the big particles in different outlets, which is exactly what's shown here. So here we've got exactly the same device on the previous slide, where we've got the inlet and two different outlets, one that collects the flow that has taken the inner curve all the way through, one that's collecting the fluid that's taking the outer curve. If we want to use this as a simple particle concentrator, we work at a high flow rate of 6 milliliters and everything gets swiped to the outer curve. And you can see that all the particles sit here. If we go and use at a moderate flow rate of 2 milliliters a minute, however, the equilibrium of the Dean's forces and the drag forces is as such that the small particles are being pushed towards the outer wall, the big particles are moved towards the inner wall, which means that we can collect particles of different sizes based on the different focusing collection points. So this part of this predictable particle, part of it is trial and error where your inlets and outlets have to be. But again, these devices, you've got a microfluidic structure, you have a pump with a certain fixed flow rate, and without the presence of any membrane, allows you to either exclude all the small particles because they all go through one outlet, or it allows you to separate bacteria from mammalian cells to have a cleaner culture happening. So to summarize, we've got a whole range toolbox full of different techniques that use the different forces. We've got the straight channels where we started off, where we've got the different focus in inertial focusing nodes. We then have the contraction expansion, where we got our small particles to just follow the sides, but because of the pressure points caused by the expansion contraction tracks, the circulated tumor cells were swept to the middle, and we could then collect the big ones from the outside, and the small cells from the outside, and the big stiff circulating tumor cells from the inside. We didn't go into any of the serpentine, but if you use complex channel geometries, we also get preferential agglomeration of small particles at at the outside, and the bigger ones on the inside. So there's a range of different structures being made there. There's the spiral devices, where there's a couple of different options where with the flow rate you can either put all particles together, have it working in filter mode, but if you tailor the flow rate a little bit lower, you can actually selectively collect one particle type at one wall and the other particle type at the other wall. And then of course there's a whole range of ways that we can mix and match different approaches, active and passive particle separations together using a Lego-like approach. Then we've got a way that we can change the fluids. So that's using a viscoelastic fluid, which the best known one is saliva. So there's a long polymer added, which means that we add viscoelastic effects to our separation system. And in contrast with the focusing node that we had with our normal inertial fluidics, in viscoelastic systems, the particles focus in a spaced manner in the center of the channel. Here we've got a couple of examples of where we can, how viscoelasticity has been used. Here the viscoelasticity is provided by PEO, which is a long chain polymer. Normally with viscoelastic flow, the particles will be concentrating in the middle. But if you use the sawtooth structures, it pushes the force field to the outside. So here we can have the red blood cells that come in from the sample, all being pushed by by the pressure implemented by these sawtooth structures. The red blood cells are all pushed to the outer wall, which means that from one outlet you can collect all your red blood cells, and from the other outlet you get a nice clean plasma sample where you can do your chemical analysis on. The same reagent PEO was also used in a very simple structure here to separate, to concentrate bacteria from microalgae. The bacteria were focused in the middle using the viscoelastic effects, whereas the algae were not impacted and pushed to the outside. So we have a system where the minimum energy part for the bacteria is in the center, the minimum energy point for the algae was on the outside, and you use different outlets to separate, fractionate your heterogeneous sample into separate fractions. A last trick is that you can kind of extract large blood cells as well into a viscoelastic medium. So here we've got a normal fluid and a viscoelastic fluid flowing adjacent to each other. The viscoelastic forces drag the large particles in without impacting on the small ones. So that allows you, if you've got a combination of circulating tumor cells and normal blood cells, the circulating tumor cells are larger and stiffer, so they will experience a much stronger pull into the viscoelastic medium than the other smaller blood cells. And that way you can separate two different particles, two different cell types based on their size, using a viscoelastic acceptor phase. Here, a viscoelastic microfluidic device was used for the diagnosis of sepsis by focusing the bacteria down into a smaller volume and then making it possible to detect the viscoelastic properties. So here we've got the outlet of the channel. So this is the whole device. We've got the inlet for, where does the sample come from? Yes. So we've got the viscoelastic inlet and the blood inlet coming here together at a first focal point and then going to the outlet. If we look under the microscope here, this is the outlet. So the focused bacteria here we can see in the middle, and they go straight through the central outlet, whereas the clear liquid can be obtained from the outside. We can then do a testing of the bacteria in the concentrated sample coming there out of the central channel. There is a couple of other ways of sorting technologies. There is ways of just using a weir-like structure where large particles can't get through, but smaller ones can. Again, if you've got a microchannel and you want to only, you can flow in one direction and allow your small particles to go to another channel, whereas the smaller ones can't. You can use a pillar-type structure to pretty much work as a filter. Most of the fluid can get through, but some of your particles will get stuck if they don't fit through the pillars anymore. Cross-flow filtration, as we know from normal filtration, you can also do at a microfluidic scale. You just put a couple of pillars in there, the flow goes perpendicular to the filtration direction. Most of the flow will be carrying along the particles, preventing the filter from getting blocked. But small particles and the particle-free solutes will be leaving the device for the small channel for further processing or detection. Deterministic lateral displacement we already talked about, and there's hydrodynamic effects that we can use as well by squeezing the flow down from the sides. This is the Lego blocks approach where we can combine them together. I think we want to move on to the next lecture. So we've got active and passive methods, where the active methods have the advantage that they provide very precise control, but they typically have low throughput and require extra devices. The passive methods are very simple and high throughput, but they require an understanding of the physics and requires complex channel design, and therefore lack flexibility because you can't change the design while you're doing the experiment. So other than the flow rate, there's not much you can do unless you make and design a new device. And then there's the viscoelasticity, which is very simple, very low cost. It's got good focusing performance, but a lot of the viscoelastic phenomena are not well understood. So it's more so observational, like the sawtooth device that we showed. It's not well understood why all the particles are being pushed to the outside. So there's still a lot of research to be done to properly understand. And there may be some consequences if cell populations need to be reintroduced into the human body, that the PEO as a polymer may not be the most friendly and may need to be removed after processing. So if you add a polymer, that may potentially compromise the usability of the product. So great if you separate something you want to throw away. If you want to reintroduce it in a biological system, that may become problematic. And then the last slide is a couple of references. So these are the different tools that we have to separate particles of different size, density, and geometry. And again, it's a toolbox. It's not necessarily that there's one is better than the other, but for each application there will be one more suitable than the others. So you need to come up with your problem, look at the toolbox, and then pick the right screwdriver. Happy to answer any further questions. And if not, it's time for Professor Malik to talk about solid phase extraction. But we may want to take a short break. I'll leave that up to you.
Here we have just focused on the analyte particles.
Yeah, so the analyte here mainly was, or the analyte here was the particle.
So good afternoon to all of you. As Professor Hussain was saying that it is difficult to pre-concentrate or to separate the viruses from the algae, and similarly there are many other methods, that is from the beginning, that we need some pre-concentration, or means to increase the concentration of the substances for the analysis. And there are many methods by which we can increase the concentration. You can listen to me. There are many methods by which we can increase the concentration of substances for the analysis. Now, for the analysis of substances, two things are very important. First is we should get the clear, pure substance, that it should be free from the impurities, it should be free from the interferences. Means it should be free from the interferences. It should have no interference in the analysis, during the analysis. And second thing is its concentration should be so much that we can analyze it. We can analyze it means it is within the detection limit of our instrument. That our instrument on which we are working is so much sensitive, so much is capable of detecting the substance at very low concentration. Because you see day by day impurities at very, very low trace levels are increasing. Many substances are present at very, very, viruses are present, as I was saying, and metal ions are present, and many other pesticides are present, drugs are present. All drugs we don't need for our safety. All drugs we don't need for our safety. So some drugs, they are not required for our body. So for this, the question is, that is from where the sample, from where we need to apply the pre-concentration. That is from where the samples are coming. And you will find that from the environment, from the wine, from the drugs, from the pesticides, from the food, all these things are contributing for the pollution, or they are going to deteriorate our environment. Like this industrial pollution is very much, and drugs are there, and from the environment and in food. So that is our sample. It can be in the food, in the cosmetics, in the biological tissues, environmental samples, various like metals, titanium dioxide, silver, iron oxide, silica, gold, and wine and other food stuff. Like for all these things, the sample preparation is very, very important before the analysis. And analysis, it depends on particle size, distribution, concentration, composition, and shape. Now, there are some of the techniques by which we can carry out direct analysis, like ICP-MS. Some of you have heard of ICP-MS. You have heard ICP-MS. Using ICP-MS, like if in your sample cadmium is present, zinc is present, copper is present, then you can directly analyze these samples. Means there is in ICP-MS also there is interference of other substances. Means there is interference, but for most of the metals, ICP-MS is suitable for the direct analysis. And phase separation, and then is extraction of nanoparticles, matrix decomposition, and pre-concentration. So these steps, these are done for the analysis of the samples, and different techniques like AFM, XRD, DLS, HDC, SEM, TEM, for different materials they can be applied for the analysis. So I will try to introduce you to the most of the advanced sample preparation techniques for environmental analysis. There are many techniques, and by which you can analyze the samples below the detection limit of your instrument using these techniques like solid phase extraction, solid phase micro extraction, and hollow fiber liquid phase micro extraction, and other is computational methods, functional materials. Functional materials, they have pores of different sizes, and depending on your analyte size, you can pre-concentrate these using functional materials. Other is matrix solid phase dispersion, and liquid micro extraction, and there is QUECHRS. We follow some of the parameters for quality assurance analysis, and that is known as QECHERS. So pre-concentration, you can understand. Now, what is pre-concentration? You take any method. Pre-concentration means increasing the concentration of the analyte in your solution, in your matrix. So pre-concentration means to increase the concentration of the sample prior to analysis close to the detection limit. Uh, and there are organic samples, like for example we can do pre-concentration for a non-volatile organic sample with evaporation in a solvent. And that is process. What is the pre-concentration process? If we define what is a pre-concentration process, then we can say that it is the process in which the analytes are transferred from a larger mass to a smaller volume, and the micro components, that is, they are transferred to a smaller organic solvent by extraction. Like you can see that in this is more volume. Now if you decrease the volume, then this analytes volume is decreased. That is, they are present in a smaller solvent volume. This is known as pre-concentration. This is pre-concentration, that is, analytes, they are present now in a smaller volume. So there is a long history of micro solid phase, these extraction methods, and how most of the students who are with organic chemistry, they separate their prepared materials, or they purify with the help of column chromatography. And so the main milestones in the development of solid phase extraction, like in 1950s, in very earlier pipes, they were filled with activated charcoal. Now if you see what is the best material for your adsorption studies, anyone can tell me? The best material for adsorption studies is activated charcoal. It is the cheapest material. Silica or other modifications are done, these materials came later on, but activated charcoal is the best material for your, because it is carbon, and carbon is non-active, non-reactive, and it is not reacting with other chemicals under the normal room temperature conditions, right? And in the late 1960s, various porous materials were introduced, and in 1970s, silica was considered, and in 1980s, short pre-column materials were introduced, and in 1989, particle loaded membranes, they were used for the extraction, and in 1992, solid phase micro extraction was invented, and it was brought to the market. And in 1994, molecularly imprinted polymers, they were introduced for the extraction. And in 1990s, like multi-wall plates for high sample processing, they were introduced, and many more techniques, they were introduced for the extraction. I will introduce you all of these techniques for the extraction. So for chemical analysis, what we need? Like if you have vegetables, you have fruit, meat, or you have lemon, that is, and you want to measure contaminants like mercury or lead in food, what you will do? if you have mercury, lead, or other contaminants in your food, then you have to prepare your sample with acid, with the heat, acids and dilution. If you are doing metal analysis, I'm saying metal analysis, then you can use heat and acid. But if you are using if you are carrying out your analysis for the organic pollutants like pesticides or PCPs or other hydrocarbons, then you cannot use acid and heat. Then you can analyze the metals using your with a suitable technique. So question is, if we do not prepare samples, means if we do not make the sample ready for before analysis, what will happen? Whether you will be happy or not, whether the results will be accurate or not. This is the question. That is, for preparing the samples before injection into the instrument. Injection into the instrument means taking the sample for analysis. You take any technique. For that, you have to prepare the sample. That sample should be ready for injection. Means it should be homogeneous. It should not be heterogeneous. If you take heterogeneous sample, concentration will not be uniform. Means if you take heterogeneous sample, mean either it will settle down, or the analytes they will settle down, or they will be non-uniformly distributed. So it is not nice to inject the sample before the analysis. So this is the question, that why do we need sample preparation? That is, analytes, they are contained in a complex sample matrix, and we must separate them. And like if we are carrying out MS, or we are carrying out HPLC analysis, like we want to analyze only few peaks of the sample, but in our sample we find there are coming so many peaks, and which are unwanted peaks. And there must be many baseline interferences. Now, like this peak is baseline interference, and this peak is many baseline interferences. Now you add your analyte to it, and they will interfere in your analysis. Means you will not, they will give you higher amounts. So another thing is that the particulates, they may limit the instrument, and your analysis time will increase. If you are using chromatographic methods, then plugging of the columns may take place, and analytes which are contained in a complex sample matrix, they complicate the analytical results, and the sensitivity of the instrument will not be very high using non-prepared samples. Like if you see this one you get only a small peak if you do not prepare your sample, and if you pre-concentrate it and using a chromatographic method, then you will get a more uh, uh, detectable peak, and this peak will be, you can analyze it. So similarly, if you are analyzing like a protein in a complex sample, then there are small peaks, and if you precipitate the sample, precipitate the proteins, then about lot of proteins, they are lost and analysis is not possible. So using precipitation, like 80% of the ion suppression takes place. And if you take solid phase extraction, I will come to you what is solid phase extraction, then you can see that there is about 100 or 200, there is a lot of peak increase, and this shows that pre-concentration step is necessary. Another thing, sample matrix cleanup is taking place, baseline interferences are removed, and if you are using mass spectrometry, it reduces the ion suppression in the MS, and the pre-concentration processing, in pre-concentration, the sample processing step makes you ready for the injection for HPLC, GC, UPLC, GCMS, LCMS, atomic absorption, and other methods. There are for pre-concentration methods, like there are 3 types of pre-concentration techniques. That is, first is flow through the equilibrium and pre-equilibrium. Another is batch equilibrium and pre-equilibrium, steady state, exhaustive and non-exhaustive. We can divide it into flow methods into 2 types, exhaustive and non-exhaustive. And exhaustive, these I will explain as you will come: purge and trap, Jordan trap, solid phase extraction, supercritical fluid extraction, and PFE method. And another non-exhaustive is the in-tube SPME method. Another is batch equilibrium. It is exhaustive and non-exhaustive. Exhaustive methods like liquid extraction, Soxhlet extraction, Jorbands, and microwave assisted extraction may be taking place. And non-exhaustive, headspace, liquid micro extraction, and solid phase micro extraction. And steady state exhaustive and non-exhaustive extraction method are the membranes. You can prepare different membranes, and using those membranes you can carry out the extraction. And first is that is miniaturized solid phase extraction technique. Miniaturized means that is only on a very small scale. Solid phase extraction methods, that is, this includes SPE, solid phase extraction, SPME, magnetic solid phase extraction technique, stair bar stair bargeoptive extraction, and immunoaffinity solid phase extraction, and micro extraction in packed syringes, and dispersive micro solid phase extraction. So, like you have a sample, what is the procedure for the solid phase extraction? That is for calculating the recovery, that is how much of the analyte you can recover. You have a blank sample matrix, you add analyte to it, spike to it, then using that is spike is done, then you carry out the solid phase extraction and analyze the extracted sample, and from the recovery of the extraction, that is 100 into response of the extracted sample and response of the post extracted spiked sample, that is from the comparison of two we can find the recovery of the substance, and we can also find the enrichment factor, that is the concentration of the analyte metal like and concentration of the normalizer, and Cm over Cn, that is the baseline noise, or enrichment factor is final concentration over initial concentration, because enrichment factor is the equilibrium between the substances adsorbed on the column and separation. So make the sample clean. Analytical scientists, mainly they are trying to develop for gas chromatography, for HPLC, various techniques for the enrichment of analytes, and for this there is a signal that is for the signal enhancement at the baseline. So many techniques are used. One of the technique used largely by us also is the solid phase micro extraction technique, and this is a very simple technique. In this the fiber, there is a silica fiber which can be modified by various substances, and there is modified syringe like instrument. Fused silica fiber is at the base and cylindrical geometry. It is connected to a stainless tubing, and the silica fiber is coated with a thin film of several polymeric stationary phases, and the fiber assembly is reusable and replaceable, and small size cylindrical geometry of the fiber. It offers various advantages into the that is, it can be employed either in the sample, or it can also be employed using head space. I will tell you what is head space analysis. Various advantages is that for SPME is that it is organic solvent free. We do not use any organic solvent because it only involves adsorption. Highly sensitive analytes, they can be it can be applied to the ppm ppb range, short extraction type, and easy to use, and it do not require any other sample preparation method, and it can be easily automated. So for the analysis, HPLC is the simplest technique for high pressure liquid chromatography, and in the coming lectures I will also introduce you to the liquid chromatography and the various advantages that simple to operate, fast, highly sensitive, applicable for qualitative, quantitative purposes. Small sample size is required and wide spectrum of application, and it is applicable to polar, labile and non-volatile compounds, and high efficiency, more flexible in operation parameters, and reusable columns, and safe to use. So I will show you how we can attach HPLC to this is the SPME HPLC hyphenation attachment done in our laboratory, and this is the SPME holder, and in this it is the online process, that is during the analysis the sample is dissolved in this desorption chamber. The mobile phase which is coming from the reservoirs dissolve the sample, and it is subjected for analysis. So like it is the desorption, it is the injection valve. We we don't need to need any other we do not need any other solvent for the desorption of the substances, analytes, only the mobile phase which is used for the analysis, and so we can use for the direct analysis using SPME at a very low level, that is at ppb or ppt level, using SPME. And for space analysis, like you have a vial, and in the vial you just you do not dip the fiber in the sample, you just hold the sample above the liquid surface if your sample is in the liquid state, or if your sample is even in the solid state. If it is volatile, then it is very good. If it is not volatile, then you little heat the substance and it will be adsorbed on the fiber surface, and then you can make its elution in the desorption chamber. So we have this is the commercial SPME device, and this is the lab made SPME device in which we have taken a silica fiber, and we have done the various polymer coatings on this fiber surface, and it is we have made suitable for the analysis. So using SPME, that is we can have a monolayer coating, or we can have a bulk coating, or we can have a coating on the capillary. Then it is known as polymerized material, that is in tube coating. So we can directly inject the sample inside this tube, and the sample can be in the first step you don't connect this to the rheodine valve, and after that replace it, and after allow the sample to pass through it, and when the sample is adsorbed on it, then inject a volume of the solvent, or you pass the mobile phase through it, and online desorption will take place. So I have already told you that that working with SPME, and in the market different category of fibers like PDMS, divinyl benzene, PA, polyacrylates, and carboxene, carbovax, templated resins. They are available. And like this I told you, that is headspace method and the direct immersion mode. That is, in headspace method you just hold the fiber tip on the surface, and in the direct immersion mode you dip your fiber into the sample, and this is how the inside of the desorption chamber the desorption takes place. So we have used HPL, SPME for the analysis of explosive materials like RDX, HMX, TNT, trinitrotoluene, and tetrail. And you can see the nitro explosives and HMX and TNT. You will find that these substances or matrices, they are very difficult to, their samples are very difficult to prepare for the analysis, and so there is metabolites of TNT. You can see we can extract all these metabolites on the fiber. So we have performed various, we have developed various methods, and one of our this article, and it is almost half of the journal was published with this, means it is 37, that is 9 pages of the article, and it describes all the methods, approaches for the analysis of explosives. Because for the extraction of explosive materials, that is RDX, TNT, very few methods are available. So for selecting the method, like you have to select the suitable wavelength for RDX and HMX, and we can analyze these substances using a suitable wavelength of their maximum absorbance, and we can separate HMX and RDX using HPLC, and we can pre-concentrate the materials using SPME. And the best thing was done by us, that we used the surfactant solutions for the removal of pesticide, for the removal of explosive materials from the surface of fiber. That is, these materials were adsorbed on the surface, and then we used the mobile phase, which is containing a little SDS. SDS is sodium dodecyl sulfonate, and it is a surfactant, and it was used for the analysis. And so that is HMX and RDX. They were well separated, and you can see we can do their analysis in at a very low concentration of 50 ppb, at a very low concentration of ppb. I will tell you one example, that in close to Chandigarh there is a explosive manufacturing unit, and there is a lot of RDX, and is manufactured. There is a RDX army unit, and there is a army you can say factory, which is ordnance, which manufacture RDX, and they say that RDX is not present outside their premises, and but we analyze the water which is present outside their factory, and we found that RDX in it was present in sufficient concentrations. So I will, that is different methods they were developed at very low concentration. You see that is at very low concentration you will see at 20 ppb, 20 ppb, 20 ppb parts per billion. You can see how much low concentration of explosive materials these were detected, and this work was done by the in the DRDO project, Defense Research Development Organization. They sanctioned us a DRDO project, and we developed these methods for their analysis. Now I was saying that this interference, that is like this interference is coming, but we cannot remove this peak from the samples at a very low concentration. So they were these RDX and HMX samples, they were analyzed. Like we have all the explosive materials, they were separated and they were analyzed, and that is all the metabolites of TNT and RDX, they were analyzed using suitable concentrations of these. Instead of HPLC, you can use SPME for the gas desorption for gas chromatography also. If you inject your SPME fiber, SPME needle into the gas chamber, gas that is heating unit, then which is above the column, and then it will dissolve the fiber, it will dissolve the explosives from the fiber surface, and then they can be detected by gas chromatography using so many explosive methods were developed for the explosive analysis. And for the extraction of for the reading on the solid phase extraction, there are two books, that is Solid Phase Extraction by E.M. Thurman and Nigel J.K. Simpson. These two books are available. Another is micro extraction by packed absorbents, and you see this is a cylindrical, this is a syringe, and in this is the packing material. This packed material, on this packed material you can modify it. It is a very miniaturized technique, and you can use it directly for HPLC, or you can use it directly for the gas chromatographic analysis. So MAPS, it is called as micro extraction in the packed syringes, and a very low amount of sample can be used, and ejection can be done at very low concentration. So there are many advantages of MAPS, that it reduces the time for analysis, and volume for analysis is used is only 3.6 microliter, and it can be fully automated, and it eliminates all the extra steps which are needed for the sample preparation and injection. So that is, we can use maps, and it can be modified by different methods, and in the desorption chamber using gas chromatographic conditions, directly maps can be used for the MS also. That is, we have used for the fragmentation of the nitroaromatics on GCMS, and you can see that all these fragmented products, all these fragmented products which are present in the environment, means like if you take nitriles or terryl or dinitrotoluene, they don't remain in the environment as such. They undergo degradation, and it is necessary to identify the degraded products, and we can identify the degraded products using GCMS, and this can be applied, maps can be applied. So this is how we have studied various, if you can tell me the time, if 4 o'clock.
5 minutes.
And then you can pH or solvent, or you can select the different conditions for the analysis, like we have analyzed using maps all these tetrayl 2-amino DNT products, TNB trinitrobenzene, all these means these can be analyzed at a very low concentration.
We have this facility, sir?
Yes,
You have this facility.
we developed this many times, and you can see we have generated this data for the analysis, and about 10 PhD students, they did their maps and SPME technique used, and one of the student, she went to Canada also, did her postdoc, and now she is employed in an institute in Canada as a professor. So you can see that we have that is calculated the limit of detection and the limit of quantifications. They are very, very low level, and we were trying every time to reach at the lowest possible limit. So I will move to like another technique. We have not used this. Some like there is Sandeep. He has used this stair bar adsorptive extraction. They have made nanoparticles, and they are stirring it and adsorbing the analytes on the nanoparticles, and so from fruits and using various modifications, these can be stair bar adsorptive, stair bar adsorption can be done, and after that using a solvent, that is you can see that is you have this extraction. We extract it from the water and pre-concentrate it. All the analytes, they are adsorbed on this stirrer, which is made of adsorbing material, and later on with the desorption we can elute it, and we can use it for the analysis. So another thing that is you can see that SEM and TEM they have been used for the modification of the materials which were adsorbed on the stirrer. So you can see that is how the pre-concentration is. That is, this is the baseline, and in the baseline you don't see any analyte, and after the pre-concentration, like you can start observing these analytes. Then at different concentrations you can see that is using a very small volume extraction can be done, and analysis can be done. And another is magnetic particles. They are used for the solid phase extraction. In this iron nanoparticles, they are used for the adsorption studies. It is similar to stir bar absorptive extraction. And another method is the immunoaffinity solid phase extraction, that is in which resin is having affinity for different proteins, and they can be extracted and they can be analyzed. And another is a single drop micro extraction. Single drop micro extraction, in brief, I will tell you, that is, we take in a syringe, gas chromatographic syringe, a drop of the little solvent, non-polar solvent like toluene or hexane or chloroform, depending on the solubility of the analyte, and we heat it, and then we can, after the extraction, inject it upwards and directly inject the sample into the GC gas chromatograph or into the HPLC, and it mixes with the mobile phase, and analysis can be done. So different, like this is the single drop, and you can do it by the head space. Head space means you are using it above the sample, and indirect it is within the sample, because if sample is water, your organic solvent, and this small drop will not fall, means you stir it, adjust the speed of your stirrer, and that is, you can, that direct immersion, single drop micro extraction, and head space, you can adjust it, and you can inject into the HPLC or GCMS, like this is the injected in the HPLC syringe, and if you have a GCMS oven, you can inject it. And this is for MS magnetic liquid phase micro extraction for gas chromatographic, that is nanoparticles, magnetic nanoparticles are used, and after the extraction and desorption can be done, and they can be analyzed. So another is there are some solvents which change into solids, solids, like we have a this is our analyte, and it is in a solvent. We add some solvent to it, that is dispersive liquid micro extraction, and then we cool it. The this extracting material, this liquid, this dispersive solid which we have added, it will absorb all lights, and it will, when we will put it in ice, it will solidify, and just you drain off the upper liquid and you are ready for the analysis, or you melt it and the analysis can be done. And another is direct liquid micro extraction, that is, this is developed in the last decade, and you can see that is after the sonication, this sedimentation will take place, and you can inject it, you can take it out, and you can inject it. Another thing that is using nanoparticles, as I told you, or these can be modified with various various fullerenes or some other carbon aromatics like magnetic nanoparticles. They are modified with silica dots, and so by this way different approaches they can be developed. So all liquid micro extraction techniques like single drop micro extraction, dispersive liquid micro extraction, or liquid micro extraction, they can be classified and they can be used. So and direct liquid micro extraction, what I told you, that is we insert a small drop of the liquid, and then we extract it and separate it. Nowadays another thing is coming it, that we are developing molecularly imprinted polymers, and these are molecularly imprinted polymers that are highly specific for a particular analyte, and we create the cavities in the polymer, that we create the cavities in the polymer of the size of analytes, like these cavities, these analytes are removed later on, and these cavities are created, and on these cavities the analytes, the material which can fit into these cavities, they can be analyzed by desorption. This is just like the pant and shirt of a single person who can use it, and no other person can fit into it. So these molecularly imprinted polymers, that is, they are highly selective and sensitive for the analysis of drugs. I will show you that. Look in this polymer, this small cavity, it is so very good. I was surprised that how these cavities are created in the polymer. And you look here, that this cavity. Similarly, there are this cavity, that there are cavities in the polymer, and analytes, they can, when we add them to the solution or to the sample, they very specific from the environment. They fit into it and they can be analyzed. So this is the summary for all the methods for the micro extraction techniques, not in detail but a brief introduction to the methods. And I will next time we will show you how to use HPLC and gas chromatography is not, but we will have a journey with liquid chromatography, how to use it and how to apply the solid phase extraction for the analysis of analytes. And I will have try to do mass spectrometric calculations to find out the unknown substances. Thank you very much.
My own setup, maybe certain beaker, or where I have a liquid, I just want to analyze its volatiles at certain specific temperatures.
Ma'am,
How that sample will be injected?
no,